Is there like trying to get the video working on this, but it doesn't seem to be. Is there like a filter?
It might have been closed, but
Yeah. Oh, there we go.
okay, yeah,
That seems like it's
this
working.
is so sweet.
All right. Yeah, because I think this is what's going to the it's really flickering. All right. Well, this is what's going to the live stream, but
Okay.
it's. I think we'll hopefully it'll work. Let me get back to where we were.
Which mic? Check, check. Is it? Can you hear me now? Coming in okay?
Okay. Sounds good. Yeah, sure thing. All right, welcome everyone. Please have a seat. We're going to get started in just a couple moments as soon as everyone can grab a seat.
Yeah, yeah. So I work at like math or smart maybe. I haven't done anything in CFS like that. Just a little bit of stuff with like our object storage stuff that we had to spend in it. Yeah, so I help out a little bit here and there with what they need. I haven't been people jumping in it. Yeah. I've worked with Brian at a store like 10 years ago. I was there for like 2-3 years, and then I joined up with that. Like I gave talks about sales and stuff. Yeah. Yeah, it's fun. Yeah.
All right, grab a seat. Welcome to the 2023 OpenZFS Developer Summit. I'm glad to see you all here. So first, I wanted to give some thanks to everyone who helped make this conference possible. Karen couldn't be here today. She's traveling, but she did a lot of the behind the scenes work as always, I think. And Victoria, again, helping us with sponsorships. And Ala, new to the conference this year. I think she just stepped out, but you probably saw her at the welcome table. One note for those here, if you need to leave the building, then let Ala know so that she can be there to let you back in. Or send a message on Slack. All the attendees should have gotten an invitation to join the OpenZFS Slack. So feel free to post on there, and I or someone will see it and be able to let you in or let you out of the elevator if you're stuck in the elevator, or any other logistic problems. Feel free to post on there or message me. And thank you again to Aaron Holding, who designed the awesome graphics that are on your t-shirts. Does anybody know what this graphic is of? I know you know. Yeah? Yeah, the Sutro radio tower, which was, I think it's 50 years old this year. And when it was announced and first built, it was perceived as the eyesore of San Francisco. Like the San Francisco Chronicle wrote articles that were like, everybody hates this thing, why are you putting this thing up? And now it's become like a symbol of the city and the city's infrastructure. And we love doing infrastructure themed t-shirts, and because I think OpenZFS is a really cool piece of infrastructure. All right, thank you to our sponsors who made the conference possible. So our diamond sponsor and my employer, Delphix, thank you very much. And our gold sponsors, OS Nexus and Clara, thank you. Our silver sponsors, the FreeBSD Foundation and Synedo. And our bronze sponsor, IX Systems. Thank you all. I know, the macroeconomic forces are not really in our favor right now. It's not easy to, make a contribution and get only recognition in return. But we really appreciate the companies that have been able to continue sponsoring us this year. All right, so what's new with OpenZFS? Did anybody see the announcement last week about the 2.2 release? A few people. All right, well, for those who don't know, there's a new release of OpenZFS. I think the last major release was 2 years ago, almost exactly. So major new release, lots of cool new features. I realized actually all of the headlining features from this release have had talks at past conferences. So if you're interested in these cool features like block cloning, Powell actually gave two talks, one last year and one several years ago. One, the Linux containers, we're gonna have a talk about that today. And then other ones have had talks from past years. So if you're interested in those, the video recordings are all up on our website and on YouTube. So you can learn all about how these features work and why we did them. All right, so today you're gonna hear about some more cool features in ZFS that may or may not be actually part of a release yet, but hopefully they will be a future release. Couple of points of logistics. Lunch will be at 12:30. We have quite a while for that. It'll be served here. We'll have a reception around 4:30 in the area over there. And then tomorrow we'll have a hackathon. It's gonna be same location here, starting at 9 o'clock. You have opportunity to work with people from the community that you might not normally see. I think we have a couple of good ideas of projects that can use collaborators. So if you don't know what to work on, maybe if you're not like a C kernel coder, there's still lots of cool stuff for you to work on. The community is not just like code running in privilege mode. There's a lot of other code. There's a lot of documentation, website, project planning. Putting on this conference, for example, is a non-coding activity that I have done a lot in the past and I could use some help with in the next years. And lastly, OpenZFS, we have a code of conduct that applies to our online interactions as well as the conference here. You can read it, but it boils down to be kind, be welcoming. Please recognize that people come from different backgrounds than you might. If you have any problems during the conference, feel free to reach out on email or to reach out to me. And lastly, you can find us on OpenZFS Slack. So with that, I will introduce our first speaker, Alan. Right, yeah, right, here he comes. Let me get his slides up here. Okay, I think that is this how we were doing it, or was it in the other?
No, this is fine.
Okay, are you sure? Is there one? Okay. Is this going to work? How do we get it full? I had it full screen before. Do you remember how I? Oh, there we go.
This
It's
is a
working.
file, not a. Okay.
Is that going to work for you?
Yeah.
Okay. All right. There may be some way to
This-
full.
what we're- Oh, there it is. Just
Oh, this thing. Yes. Thank you. Okay. Excellent. All right. Take it away, Alan. Thank you.
Yes, good morning, everyone. My name's Alan Jude. I'm the CTO of Clara, and I've been a ZFS developer for quite a few years now. And today we're going to talk about fast dedupe, collaborative redesign for dedupe that will hopefully make it much, much faster. And I'll be able to show some results from our early prototype today. So quickly going through the agenda. First, we'll talk a bit about what makes dedupe slow in the first place. And look at the data structures that dedupe uses and how we've optimized those. And then introduce the crux of our performance improvements, which is log dedupe, a way to amortize the cost of having to keep all the hashes on disk. And then we'll talk about some of the ancillary features that we've added around this to ensure the performance stays high as you get an older pool using fast dedupe, using quotas and zap shrinking. As well as being able to prune the dedupe table in order to, if you only have so much space available in a special VDEV or in RAM for the dedupe table, how we can decide which entries to remove to let new entries in and increase the chances of getting duplicates. And dedupe preload, so that if you have a system with a large amount of dedupe, that your performance after a reboot or failover isn't terrible for multiple days. Then we'll get to the exciting stuff with the benchmarks showing what we've managed to achieve, and then talk a bit about what else is still out there to do. And then I'll take your questions. So starting off with what makes dedupe slow, the first thing is that every time we're going to write a new block, we first have to check if we've seen that block before. So after the write comes in from user space and ZFS runs it through the ZIO pipeline and generates the checksum, we then look up that checksum in the dedupe table to see if we've seen this block before. Because if we have, then we don't need to allocate new space on disk. We can just write the block pointer pointing to that existing allocation and increase its reference count in the dedupe table. But this means for every write we do, we have to do some random reads to pull that information out of the zaps that are the dedupe table. And currently, the dedupe table is made up of two separate zaps, one for blocks that are unique, so have not deduped yet, and then a separate table for ones that have deduped. So when we want to check for one particular hash, we need to check both of those tables unless we find a match first. So if you're doing a single 4K write, you might have to read multiple indirect blocks and then an L0 block from the zap for the unique table. So maybe 3 or 4 reads there, all randomly scattered across the disk. And then if it wasn't a match there, you have to do the same check against the duplicates table, which might mean another 3 or 4 random IOPS. And so suddenly to do one write, you've done as many as 8 or more random reads to see if we've seen this block before. And that's the main thing that makes dedupe very slow. Part of the reason why blocks are so random in the zap is that for performance of lookups, the zap is sorted by the hash, the checksum of the blocks. But that means if you write 4 blocks, the way hashes work means that those should be very different hashes each time. So you're going to, if you're writing 4 blocks, you're not going to benefit from the reads you just completed for the first hash when you're doing the second hash, because it's going to read some very different part of the DDT. And so unless you have an extremely large number of blocks being checked, you're not going to get much cache efficiency from the dedupe table. And so your reads are going to be very randomly scattered throughout the dedupe table. That can be helped by, if you can keep the whole dedupe table in RAM, then you're going to get much better performance because you're reading out of RAM instead of off, especially a slow hard drive with very limited IOPS. But for that to work, your DDT has to stay small enough to fit in the ARC and not push all of your other data and metadata out of the ARC. And so that's where, from the agenda you saw, we talked about putting a quota on that size and being able to prune some entries in order to not have to just stop using dedupe once your DDT gets to a certain size. And then the other main things that make it slow are the amplification. Like we talked about, having to do a bunch of these extra read IOPS is going to, especially if you're pooled based on hard drives, sap all your IOPS doing these lookups. But also at the end of the transaction group where you birth these new blocks, we have to add their hashes to the dedupe table or update the existing dedupe table entry to have a higher number of references now. And so again, that's writing an L0 block and then all the indirect blocks up to the top for it. So again, a 4K write on top of maybe generating as many as 8 read IOPS is going to generate at least 3 write IOPS. And so you very quickly run out of IOPS, especially when the indirect blocks get larger. And then finally, just the total amount of extra bandwidth you're writing, right? Even if you're not running out of IOPS because you have NVMe or something, if you're having to write a whole lot of extra blocks, you can end up writing 2 to 10 times more data to the disk as metadata about dedupe than you did actual user data during each transaction group, and that can eat all of your performance. So these are the main reasons why dedupe ends up being slow. Some of them we can fix, some of them not so much. So looking at the actual structure of dedupe, so on disk, that zap contains basically a key structure, which is the 32 bytes of the checksum, as well as 8 bytes of properties, whether, what compression algorithm it's used, what its physical size was, what its logical size was, and a couple other bits. There's quite a few unused 0 bits in the middle there, but not enough to shrink it. And so that key is what ends up being used as the key in the zap. So it also means that even if there was a collision, the sizes weren't the same, the blocks would still have a different key in the zap. And then we have the actual entry, which is 256 bytes, because it has 4 DDT fizz keys. So this is, each of those consists of the 3 DDAs, the virtual addresses where we would store data on disk, So that's which VDEV and at what offset we've stored the data for each of up to 3 copies. The reference count, how many times this block has been used already. And so 1 means it's not deduped, and 2 or more means there are multiple blocks using it. And we use that information when we free a block to decide if we can actually free that DBA or if it's still in use by others. And then ZFS tracks the physical birth time. So when did we originally write this block to the VDEV? But in traditional legacy dedupe, we actually store an array of 4 of these. 1 for any of the blocks written with copies equals 1, another for copies equals 2, and another for copies equals 3. And then I think it was before 2.0 or so, we also had the concept of a ditto block. If a block had deduped a very large number of times, we'd store a whole extra set of copies of it just in case. Because if we're referencing this block 100 times, if the one sector goes corrupt, we want to make sure that we don't lose the data. But it turned out that wasn't working as intended and wasn't being scrubbed properly. So a couple of years ago, that feature got deprecated and dismissed, but to avoid changing the on-disk format, the slot is still there in the on-disk format, but is now not used for anything. But that means for each dedupe entry, we're storing a lot of this information. It does use ZLE, zero length encoding compression, since of the 4 slots, only 1 is ever used to shrink it, but logically, it's still a rather large entry. So to fix that, in the new fast dedupe, we changed things around a little bit and got each entry down to only 72 bytes by just having 1 of the DDT fizT. But what we do is, if you originally wrote the block with copies equals 1, we'll populate 1 of those 3 DBAs. But if later a second block is born that does have copies equals 2, it will just allocate 1 more DBA and update the existing entry to now have 2 DBAs. So you'll have 2 copies available to anybody who used or references the same entry in the dedupe table. Slight downside is that if you delete the only copy that had copies equals 2, as long as somebody else is still using the block, we'll keep both copies. But that's a very small amount of space, and the number of people using different copies equals is pretty low, so I don't think it's a big concern. And then for the pruning feature, we've added a new entry or item to the entry, which is an actual wall clock time of when this block last changed in the dedupe table. Specifically, this is to catch the case where a block was in the unique table, and so eligible to be pruned if it went a very long time without ever getting a duplicate. But if it got upgraded to having a duplicate, there were multiple copies of it, but then it got freed and went back to being on the unique list. If we just used the physical birth time to track that, we would still think that block had never deduped when it had. So we do that. And this allows administrators to express a much more humane policy of, if this block has not seen a duplicate in 90 days, then let's prune it in order to make more space for incoming blocks to have a chance to dedupe instead, since they have a higher likelihood than a block that's gone 90 days without seeing a duplicate. And being able to express that in human time instead of transaction groups is much friendlier to the user. But the big change for fast dedupe or FDT is that instead of at the end of each transaction group updating all the entries in the ZAP, we instead accumulate them to an append-only log, kind of similar to the log space map. So after the writes come in at the end of the transaction group, we move them to a new in-memory AVL tree, again sorted by the hash of the blocks that now are pending changes to the ZAP. And we let that block or that tree accumulate changes over a long time, while as we add items to the tree, we're also appending them to this log object on disk. And then once the log gets to a certain maximum size, based on how much memory you want to spend on it, or it just gets too many transaction groups old or whatever, then we start iterating through that AVL tree and writing those changes back to the ZAP, but specifically sorted by the hash order. So we'll update all the hashes that start with 000 in one transaction group, and then 001 in the next transaction group, and so on. or whatever number, however many we can fit in a transaction group without making it take too long. You can control how many seconds it will spend writing out ZAP entries. But this allows us to make sure that we're amortizing the cost of updating those indirect blocks. We're making hundreds or thousands of changes and only have to update the indirect block once. Whereas if we were doing it the traditional way, we'd have to update multiple indirect blocks every single transaction group. And this makes it much more efficient. The trade-off is it uses a bit more memory, but that's controllable. And it has to deal with what happens when you export and import the tool or crash. So yeah, every time we end a transaction group, we move all those pending writes into the FTT AVL tree and add it to disk. And we write this appending to the log. So then at tool import, we have to read that log and recreate the AVL tree. And since the log is unordered, basically, it's written in the order you wrote the blocks, not in hash order, so that we didn't have to rewrite it. But as we build the AVL tree, it will be sorted by the hash. But the trade-off is that this ends up meaning that the importing your pool takes a bit longer. Kind of like the log space map, we have to go through this and do all of that. It may be possible to defer it somewhat, to maybe just not allow new writes, or new writes don't dedupe while it's pending, but we wouldn't be able to handle freeze, so I don't know that that makes sense. But based on feedback from Alexander, we're also looking at having a command to force the flushing and truncation of the log in order to, in cases where you're going to have to do an import soon, make sure that this happens then and kind of asynchronously, so it doesn't have to slow down your export if you're exporting manually or your import. And so as we're writing out the changes, in the bonus buffer of the log that we've been keeping on disk, when we're flushing the log back to the ZAP, we can keep a pointer, a checkpoint to where we are as far as flushing out the log. So we keep as we're walking the AVL tree in hash order, every time we stop at the end of a transaction group, we record the last hash that we flushed out to the ZAP, so that if you export and import, we can resume from that same point and not have to redo anything. And then once we've flushed out the entire log, we can truncate it back to 0 bytes and start accumulating new ones. Yes, because this is a PDF, the animation doesn't work. But to compare how it worked in legacy dedupe, originally you would have written these blue stripes out to the ZAP, and then in the next transaction group, the green ones, and then the next transaction group, the red ones. You see your writes are very scattered, all out of order, and each of those is going to touch a bunch of different indirect blocks, and the total amount of writing you're going to do is a lot more. Whereas with fast dedupe, imagine we wrote the blue blocks, and then the next transaction group wrote the green ones, and the next transaction group wrote the red ones. We've updated the ZAP with the same information, but by accumulating more of it before we do it, we're able to do it much more economically and not update the same indirect block, 10 transaction groups in a row, instead doing it just once. And so that means every time we're doing a write, we first have to check these in-memory AVL tree to see if the block is there, because it will contain newer information than is in the ZAP, because we haven't written it back to the ZAP yet. So then some of the other improvements, the first one is dedupe preload. We had a customer that's using legacy dedupe, and they had a DDT that was over 100 gigabytes. They had enough RAM for it, but they found after a reboot, it took at least 72 hours before the write performance wasn't down in the gutter. And so we wrote a command, so zpool load -t, I think it was DDT back then, but FTT now, that basically walks through the entire DDT and prefetches it into the ARC, so that they run that after import. It takes a couple of hours or something, but it means their performance is back to good very quickly, instead of taking 3+ days to just, as you randomly write, eventually cache most of the DDT back into memory. We're also working on an extension so that you could set a pool property to cause this to happen automatically after pool import. Looking at what interactions that might have with the L2ARC rebuild as well to make sure that we don't overtax the system after an import by trying to do too many different things at once. Then the quota we talked about, we want to constrain the size of this dedupe table. Now it's a bit smaller, so that helps, but we want to constrain the amount of memory it's going to take. Basically, because we keep the hash of every block we've ever seen, as you write more and more data, eventually the dedupe table gets bigger and bigger until it's, it has the hash of every block you've ever written to the pool. And once that exceeds RAM, now suddenly you're evicting from the ARC all the time. And when you go to do a write, you have to wait for a bunch of random read IOPS off a hard drive, and that will make you regret your life choices. So with the dedupe quota feature, you can set it to a number of gigabytes of RAM that you want to, from your ARC, you want to allocate for the maximum amount that the DDT can take. Or if you're using the special metadata classes, you can have a dedicated dedupe VDEV, and you can set the quota to auto, and it will constrain the DDT to the size of your special dedupe class so that it will never exceed that size and not end up spilling over into your regular storage that might be much slower than your dedicated dedupe storage. And that avoids the cliff you can fall off if your dedupe ever gets even just a tiny bit too big. But for that to be effective, we needed zap shrinking, which was a hackathon project here last year. Well, somebody built it before, but extended it a bit. And the focus of the original work was dealing with directories that had a lot of files in them and then didn't. But it turns out the zap is the same data structure used for dedupe, and we needed the same thing, but also to take it a bit further to deal with not just, the file used to have the directory used to have millions of files, and now it has almost none, and we can shrink most of it. Whereas with the DDT, we tend to be putting holes in it, and it's only 30% full now, and we really need to condense it, not just shrink the empty leads. And using that so that when you have a quota, without zap shrinking, you could never get back down from the quota, and that caused a problem. So with the quota, what happens is if you do hit the limit, it will basically act as if dedupe is off. So new blocks that get born, it'll check the duplicates table and will continue to dedupe if the block already was in the dedupe table. But if it's a fresh, unique block that we've never seen before, we write it to disk without the dedupe flag and don't add it to the dedupe table to keep it from getting any bigger. And so it's kind of opportunistic dedupe, but not as good. And so with zap shrinking means that as you delete data, you will now get space back in your dedupe table and be able to start deduping blocks again. And that leads us to the next thing, which is pruning. Since we have these two zaps, basically anything on the unique list is eligible for eviction. We could decide to delete it from the zap and gain that space back for some newer block that has a higher chance of deduping than one that's been sitting on the unique list, like we said earlier, for 90 days and has never seen a mate. The new block has a much higher chance of having a mate come in than one that's been spent a long time and never got there. This does require some special handling during a free. Normally during a free, when we see the dedupe bit set in the block pointer, we go find the entry in the dedupe table to decrement it by 1. And if it's the reference count is now 0, then we can actually free that DBA and get the space back to the pool. And there's an assertion there that we will definitely find this hash in the dedupe table. But if we start pruning, then that assertion no longer holds true. And so minor change, but a small one there to deal with that allows us to take the oldest entries and remove them. So combined with the quota, a background thread can, if we're at 95% of the quota, let's delete, a couple of the oldest entries to make sure we always have room so we can continue to dedupe always, while at the same time evicting the oldest entries that are the least likely to provide us benefit. And this way we get the maximum benefit from dedupe. And that's where the new timestamp in the on-disk format comes in handy. Because in addition to that, the user can express a policy where we will preemptively dedupe or prune any entries that are older than the example I have was 90 days. This way, even if your dedupe quota is, 128 gigabytes of my 256 gigs of RAM, if I say don't ever keep anything older than 90 days on the unique list, then it may be that my DDT will only ever use 40 gigabytes at that scale, and that the excess memory can go back to actually being cache in the ARC for my data blocks and give me performance instead of just avoiding the bad performance of not fitting the whole DDT into RAM. So to use it, it's fairly straightforward. You just enable the feature flag. We don't have it on by default just yet because it changes the on-disk format for the zaps. Well, it stores different zaps basically, and is not compatible with the legacy dedupe, and there's no kind of upgrade mechanism. It's more, if you make a new pool, you'll want to use fast dedupe instead. Most people hopefully aren't using old dedupe as it is. And then you can set your quota for how many gigabytes you want it to be, and then your policy of how many days of old entries you want to keep. And then there is currently a tunable for how much memory you want the AVL tree to be able to take. And that, right now we're defaulting to like 1% of system memory. But if you give it more memory, it'll let that amortize more writes before it starts flushing out to the zap. And it can improve performance, but the trade-off is longer import time and more memory usage. But depending on your workload, that might be a perfectly acceptable trade-off to make dedupe less expensive. So now the fun part that everybody wants to see, how big of a difference does this make? So our test methodology, have a machine where I have 2 dedicated SSDs. One is going to store the data, and one is the dedupe VDEV. It's 32 gigs of RAM and 10 cores. Our test is to write data using FIO with a 8 kilobyte record size. So we're going to do 10 rounds. Each round, we're going to create a new data set and use 8 threads to write a 4 gigabyte file. So we're going to create 4 million dedupe entries by writing 32 gigabytes of data. Then we're going to pause, measure how much we wrote to the dedupe VDEV, then do it again for a total of 10 times, writing out 320 gigs of data and seeing how, as the dedupe table gets bigger, how that affects the amount of amplification, the amount of extra writing we had to do just to that dedupe VDEV, using the counters I added with VDEV properties, which is one of the features that came out in 2.2. So here, the bright red line at the top is legacy dedupe. So as we write out more and more data, we see the amount of amplification is higher. So when we were writing the last 32 gigabytes to that pool, we wrote 141 gigabytes of dedupe updates, even though we were only adding 32 gigabytes of data. So that was 420-something% amplification. And if the trend continues, it means if you wrote another 32 gigabytes after that, you'd very quickly be writing 5 times as many updates to disk as the amount of data that you wrote. And then way down here, you can see the blue line is log dedupe. And then something I'll talk about in a minute, it turns out that the policy in ZFS is that all of these dedupe tables are critical important metadata. So we write them with copies equals 3, which is part of the reason why the amplification is so bad. So then we did a test, the next highest line there, or the kind of orange one that's in the middle, is what if we just used copies equals 1 on the fast dedupe table? So that zap, we only write 1 copy of every block instead of 3, because your pool should have redundancy, right? You're using RAID Z or mirrors or something. So you're not as likely to lose one sector anyway. And if you run a pool with no redundancy, you've onboarded that risk. And so with that, we see much better. So to make that a little more readable, I took the red line off the graph. Get old dedupe out of here. So here we see this kind of the second line, the orangish one, that is log dedupe, where we allowed up to 256 transaction groups worth of data to accumulate. There's about 320 megabytes of memory. So we usually hit that before we hit 256 transaction groups. But by aggregating up to 320 megabytes of ZAP changes at once, we see that in total, we had an amplification that peaked around 27%. So much better. One of the things we were curious about is in 2.2, we changed the default block size and indirect block size of the ZAPs used by dedupe from 4K and 4K to, I think, 32 and 32. So suddenly, the ZAP updates are actually more expensive, and that's where log dedupe has an even bigger impact. So the bright blue line at the top is actually going back to using a block size of 4K just to see what that would do, and we see that it causes quite a bit more inflation, hitting almost 40% instead of 27%. But then we tried, the purple line is the same thing, but we went to a full 128K for the ZAPs. But because you're not going to make that many changes to any one leaf block, the savings are not very much. But when we upped the amount of memory we gave the AVL tree from 320 megabytes to 1.6 gigabytes, we see that the amount we had to write out was a lot less. And we saved that much more because we update the leaf block once with all the changes instead of once every transaction group. And so with that, we see an inflation peaking at about 13%, which makes it much more usable than 450%. And so this is just graphing over the course of writing out 320 gigabytes, what was the total amount of data we wrote to our dedupe VDEV, which might even come down to affecting your wear leveling on your SSDs. So with legacy dedupe, we wrote over 750 gigs of data to the dedupe device just to write 320 gigs of actual data. Whereas even with copies equals 3 on fast dedupe, we were well under 200 gigs. And then again, the yellow is if we use copies equals 1, and we see that we're at 63 gigabytes out of 320. So like 20% instead of 250 or 300%. And this is still a relatively small pool, right? The dedupe table only went up to 40 million entries. We have customers in production with 400 million dedupe entries. And so that many more indirect blocks, and their pool's older, so it's using the small block size. So it really adds up to terrible performance for them. And then looking at the performance of this. So the black line at the top is a pool with dedupe equals off, as we wrote 320 gigabytes, and we see we get an even performance just shy of 400 gigabytes per second for a SATA SSD. But then with fast dedupe, again, the yellow line is copies equals 1, and the green line is with a bit more memory for the AVL tree. We see that we get fairly steady performance, whereas the red one, we see the performance getting worse and worse and worse as we use more and more of the time in the system to update the ZAPs instead of actually write the data that you're trying to write to disk. And down at the bottom there, where you're having amplification over 400%, you're barely getting 60 megabytes per second of writes to your SATA SSD, and you're wondering, why is my system so slow? So what's next? First is getting it all finished. So this work is co-sponsored by or led by IX Systems. So this is a team of people who've been working on this for quite a few months, and we're probably about 75% done. The initial design work was myself and Alexander Boughton, but the whole team at Clara has been working on this, including Don Brady, who's here. And we're looking for additional sponsors to help get this over the finish line. At the different sponsorship levels, you can get in on the design review and joint marketing, or even just get access to the prototype early. And so if you're interested in contributing to this dedupe work, then please check out the sponsorship form that'll be in the slides, the links in the slides. And it was on the mailing list a couple months ago. And yeah, as we get the pull request ready, then we'll be looking for that. So yes, we're looking for more people to help get this over the finish line. And so if you want to get your name on this work, then please get in touch. So like we said, we found that DDT zaps all had copies equals 3. At first, we thought that was important for the duplicate zap because, if you lost a block in there, then, that could mean the pool is just, you could never free any face ever again or something. But looking at it more closely, I think we'll actually be able to solve that. So, we've solved most of these problems for the unique zap as part of the pruning code, where we're purposely deleting entries. And so if we got a bad block in that unique zap, we could just treat it as if that block of data had been pruned instead, and we deal with that. But for the duplicate zap, we decided what made sense there is actually, I think, Matt's idea, that if there's one block of the zap we're trying to read and we get back, e checksum or EIO or whatever, we can't read that block, then we can just leak that space. It's going to be 256 L0 blocks. That's not that much in the end. And so we can just say, if we can't look up the hash in the duplicates table because that range of hashes is damaged in the zap, then we just never free that space. And so we might leak, a couple of megabytes of space in total across the pool, but it won't be catastrophic to the pool like it would if we don't add this extra code. And while we set copies equals 1 now on the zaps, we do make sure the L2 and above blocks have copies equals 2, like we do for most metadata in ZFS. And so that constrains the damage you could get down to just a small number of, basically as many L0 blocks as could be covered by all the L1 blocks, or by the loss of one L1 block. And I'd also like to give thanks to all the people that helped with this. There was a lot of people, so the entire team at Clara, but specifically Rob Norris did a lot of the work on the log dedupe part. Don Brady did a huge amount of the work on the pruning and prefetch and quota stuff. Alexander Stetsenko worked on zap shrinking. Maciej Piotrowski wrote our testing framework that has made collecting these benchmarks and doing all this stuff a lot easier. Rob Wing also worked on some of the quota and zap shrinking stuff, and Fred for leading that team. And then, of course, the whole OpenZFS community, especially the monthly leadership meetings, have provided a lot of input and ideas for this. Especially, like I said, Matt came up with some of the ideas on how to approach these problems. And Pavel is also instrumental in some of the stuff we came up with together on making dedupe and block cloning cooperate. Were also helpful in this. And obviously, Alexander Moten has worked a lot on this with me. And Rich Urkulani did some of the initial stuff that got me interested in this idea, especially around changing the block size and looking at, because we use this larger block size for these apps, suddenly log dedupe gets even more advantageous, but also we get compression. And we're seeing 3 or 4x compression on these zap entries a lot of times. Because even though we removed a whole chunk of zeros that were in there, it's still, all the hashes in one leaf block are going to start with the same prefix. And, a lot of the other, other data is pretty compressible. And, if you're interested in developing ZFS features or just getting support for ZFS, that's what we do here at Clara. So do people have questions about the fast dedupe? Mark.
So I have a question for you. You started early on pruning, it was H-based pruning where you took out the whole blocks. Do you have any data to back the assertion that says these are actually the blocks least likely to be? Seems intuitively, it seems fine, but you should know what's behind that.
Yep. So Mark's question was, do you have any data to back the assertion that pruning the blocks that have been around the longest without deduping are the ones least likely to dedupe in the future? And it's mostly just the intuition. Now that we add a timestamp there, we might be able to actually back that with data in the future to see how often that was the case. I've also wondered about keeping like a ghost list on the dedupe table to know of the, yeah, how many items were pruned that we would have deduped later. But you know, how to do that without making it as expensive as having the giant dedupe table. But yeah, we're also looking at, I think Don's looking at using a histogram to be able to figure out what the age scans are in the dedupe table as well, partly to make scanning for the oldest entries faster.
If I understand this correctly, on the right side, you have done a lot of improvement, right?
Mhm.
And on the read side, it's still depending mostly on SAP being able to link to cache. And you also reduce the size of it, like it's checking all that, right? So if I still have to put a lot of data, a single code, let's say a couple of terabytes, right? So can you come back with that map, get block size, get the table size, and do the map, but like few 100 gigabytes of memory is sufficient to hold this app in memory, or you, and if yes, if everything is in memory, then essentially you can get only that 10-20% throughput from with all the improvement on the right now.
Yeah.
Aspect of Zoom is more to it.
So the question is, assuming you have a lot of data, like 2 petabytes, all these optimizations are kind of on the writes to the Zap, not the reads from the Zap. You know, is a couple 100 gigs of RAM going to be enough to back a large pool? The biggest factor will be the record size, because that affects how many entries you can have in the dedupe table and how big it gets. But the quota also allows you to just say, you know, as we're approaching the amount of memory we have or the size of the dedupe VDEV we have, then we're going to evict entries that haven't deduped yet and focus all that storage on the entries that are deduping. Because if it's deduped 3 times, it's probably much more likely to dedupe a 4th time than a block that hasn't ever deduped. And so that's why we prune from the unique list in order to let the duplicates list continue to grow and grow.
Like that, like this. So the dedupe class that you have for the dedupe, is that like generic, I mean, it also supports mirroring all that, never used it, so this is the PDF.
Yes, you should. So the question was the dedupe VDEV class, does it support mirroring and so on? Yes, and you definitely want to do that. Because if you have just a single device and you lose that device, now your whole dedupe table is gone. And now you'd have to leave all of that space. And I think the top level VDEV code would still not want you to even try to import the pool because it was missing. Pablo?
Question. So the problem also about performance if you think that doesn't fit to run, right? Actually, cases where you where are suboptimal, so with the right, the free. So cases where you look at so the problem is when we do the right, we don't have the hash beforehand, so we cannot pre-fetch. That's why now it's also slow because we do all the reading in transaction when we syncing transaction. We calculate the checksum, or like when you do the right, we calculate the checksum immediately and pre-fetch entries from the then syncing transaction will be much quicker, and you don't have to fit the entire table. For freeze, we can already do that because we already have the checks, right? So we could potentially do that.
I like that idea. It's just that it helps you with ghostiness. If you have to sustain that over a period of time, even the prefetch becomes you're still blocked on that. Right? So I think I get your idea. The incoming drives before it gets logged and before it gets to the IO pipeline stages, you fetch the sample rate for DDTI stages. So IO pipeline stage already has the error. I guess it works for most of the time for the ghostiness. If you have to sustain that right through, at some point that becomes important. Just a thought.
Yeah. So Pavel's point was the main 2 bottlenecks are when we're writing, we don't have the checksum very early to be able to prefetch that part of the Zap so that when we go to do the synchronous read during the transaction write, that we can already have that chunk of the Zap pulled in. And that the same is true of freeze, but with freeze, it'd be possible to fix. We're also investigating if we could make the freeze be more asynchronous by just logging them without even looking them up in the Zap, and make the lookup in the Zap happen async in the background as we're updating the Zaps when we flesh out that part of the AVL tree, to make the freeze not even block at all, rather than just being able to prefetch sooner. And also looking at idea Pablo and I talked about of, is it possible to get the checksum a little bit earlier, or like even, it's only 1 or 2 steps. The checksum is 1 or 2 steps before dedupe in the ZIO pipeline, but would issuing a prefetch there maybe still make a difference, especially on a low latency device, by time the ZIO loop gets around to actually trying to do the dedupe part.
So if you already have dedupe, is there a migration path to fast dedupe, or do you have to like move the pool, or?
So the question is there a migration path from old dedupe? Currently, no. If somebody's interested in that, we'd be willing to build it, but right now, that's not something we have a use for.
Oh, all right.
Just one more question on the right path.
Mhm.
So the idea behind amortizing the cost of writes is that you get a lot of hits with
The same leaf block.
same leaf block, right? Which means that you should need collision, not really collisions, but adjacent hashes, which allows you to coalesce that into a single zero block, right? I assume that's also a factor of how long you are ready to keep the AVL trees. The longer you keep it, the more you can accumulate, right?
Yeah.
And what's the typical, it also depends on your workload pattern, actual data which comes in and you patch into that, right? And in reality, I think the test that you have done, I guess that it's same files being done multiple times.
No, it was just all unique data in that benchmark. So we just wrote out
Okay.
more and more data. And that's why we saw the acceleration of the amplification. If we just overwrote the same 32 gigs the whole time, the dedupe table wouldn't have got much bigger, but we would have spent all the time freeing instead.
Okay.
And so it's more benchmarks we need to do.
Okay.
But yeah, as you were saying, basically, as you decide how much memory you're willing to use for the AVL tree of the kind of accumulated changes to the ZAP before you flush them out, that will give you more and more collation as you get more of those blocks, more changes to each leaf block batched together. But the longer that log gets, the longer it takes to import your pool. And so it's a trade-off. But depending on your use case, you may be super willing to make that trade-off because we only reboot like twice a year. Or other times, like this is an HA appliance, it needs to be able to swap to the other head in less than 4 minutes. So we can't ever let that log get that big. Sure.
With the ability to prefetch fast dedupe, can you limit how much memory? What is it? It's like if you run it, it's just going to prefetch everything. Like, can you say I only really want 20 gigs of fast dedupe?
So the question is about the dedupe prefetch, where we're pulling in the whole dedupe table into memory. Currently, it just quickly scans across the whole thing. We've thought about, especially the case of what if you don't have that much RAM, or we're just causing a bunch of archivic for no reason. The problem is if you set an amount, which 20 gigabytes of it do you do? So we thought about maybe trying to do all the indirect blocks first and then the data blocks or something. So that will push all the indirect blocks into the frequently used part of the arc as you're scanning the data blocks or something. But generally the idea is you will use the quota to keep it down to a size that you want to prefetch all of. But if somebody has a bright idea on some way to express a useful policy for the dedupe prefetch, we'd be really interested in that. Mhm.
So we just don't cache
The data blocks at all.
Yes.
Yeah, that is a flag, I think makes a lot of sense. I've also wondered about just having a way to do that for any file. Say, hey, prefetch all the indirect blocks for this file because it's our database or whatever, and we're gonna use it a lot. But at boot, we want to warm up our cache by at least having all the indirect blocks. We can't it's an 8 terabyte file. We can't cache the whole thing, but we'd love to have all the metadata for this just laying around ready to go.
On the Arc side, so it still shares the same, if it's Linux, same kernel slabs and all that with the Arc. Like,
Yeah, you're actually caching the zap as it is on disk in memory rather than using some other bit of memory. That was an important difference over one of the older log dedupe prototypes, where it basically just kept everything in this one big AVL tree and rewrote it occasionally, is that was all outside of the Arc, so that memory could never be evicted. Whereas because we keep using the zaps here, if you're memory constrained and you're not using dedupe, like if you have dedupe on for one data set and that's not the busy one, we can push that stuff out and let the Arc reclaim memory for other use cases. And there was one other point I had about that.
something very different. So
One point I wanted to make was, now that the block size is larger, the dedupe compresses, so compressed Arc applies to the DDT table now. So if we have 32K blocks and they only take 8K of memory, you can cache a much larger DDT in memory now. Whereas when it was all made up of 4K blocks, if you had a 4K A shift, we never tried to compress it. And so it would always take the full amount of memory. So that's an interesting side effect of the larger block size now.
I was thinking, does it make sense to have separate kernel slabs for this? Because you would be preferring to evict these chunks, right? So it allows you not to fragment these slabs, right? So that eventually you will not be even free of space for other use cases.
So we use a separate slab for the AVL tree entries, and that you set a quota on how much memory you want to use for that. For the Arc, yeah, it's just random 32K blocks as if they're a record size 32 on your data set. I don't know if it makes sense to try to do anything different there. I do wonder with Mav's work on equalizing the MRU and MFU of metadata versus data. All the zap, I think, is considered metadata, and so that might allow you to play with policy there a bit. Do we use a separate, like, K-man for metadata versus data in the Arc?
Secondly, I'm not sure if by default, but so far only difference is to make control the station go kernel down,
right,
or not. Then not just for anything else.
I wonder if we should make sure the dedupe doesn't get included in crash dumps then. Yeah, we have time for one more.
With the increased block size, we can lay greater exposures.
No, because before we, so the question is, now that we're keeping so much kind of deferred and not written back to the zaps, how we do that is at the end of the transaction group, as part of the syncing of the transaction group, we log the updates to the FTT log on disk, so that on an HA failover, we reread that log and reconstruct the APL tree. So it'll be, your data is just as safe. The only downside is reading that log at import, say doing an HA failover, will add some time. And if your HA import time is critical, you'll want to keep that log from getting too big. But the smaller it is, the less advantage you get. So it's a bit of a trade-off there. And one of the things we're looking at is adding a command so that if you're planning an HA failover, and a normal export takes too long, and so you just force a HA, you can run this command to flesh out both this log space map, the dedupe log, etc., so that when you import over, it's going to be quick. But
Most AJ failovers are not.
yes, yes, but oftentimes there's an advantage to being able to do something.
Awesome, thank you. Yeah, so we'll have a 10-minute break. If you want to continue the conversation with Alan, please find him. Although, Alan, I need you for a couple of minutes with AV stuff for a sec. But yeah, 10-minute break, and then we'll have another talk. Thank you. So, on the audio, it sounds like it's been like pitch shifted up. So I'm wondering if it's possible that there's a setting here that.
Yeah, probably.
Okay, I'm gonna get the headphones so we can hear it.
I think it's doing 44 kilohertz and the computer's expecting 48 or something. Well, that'd be down and up, right?
Yeah, so I can hear, yeah, you can hear that it sounds
Do I
like a
sound
little
funny?
chipmunky.
Yes, that is odd.
Do you know if that's a setting that could be on here?
I think so.
All right.
Very slow. Okay, all right, it changed back to H1. How does it sound now? How does it sound now?
Better now.
Okay. Yes, I think it does sound better now.
Yeah, so it was doing 44 kilohertz instead of 48, and I guess the computer
Okay.
expected the other one.
Okay, great. Well, glad we got that fixed. So, anybody on the live stream, hopefully it sounds better now. And we'll resume in about 10 minutes.
There's a lot of discussions. Always.
All right, please have a seat. All right, please have a seat. We're going to be starting in just a moment as soon as everyone sits down. Next up, we have Jason Lee. All right, thank you. So next up, we have Jason Lee from Los Alamos National Lab talking to us about ZIA, making ZFS go even faster. Awesome.
Thanks, Matt. So like Matt said, I'm Jason Lee from Los Alamos, and I've been working on making ZFS faster by accelerating ZFS features. So I would like to begin by giving a quick background about the lab and why we care about ZFS. So for those who haven't watched Oppenheimer, the lab is a scientific research institute, and we do a lot of science, from high energy physics to chemistry, to biology, astrophysics, climatology, tons of stuff. And a lot of the science is done through simulations with scientific applications, which pump out tons and tons of data. And by tons and tons of data, I don't mean a couple hundred gigs or a couple of terabytes. I mean terabytes per second. And due to the sheer volume of data that we have, we will inevitably suffer errors from bit rot to hardware going down, anything. And to combat this, we need ways to first detect errors and then fix them. Fortunately, ZFS comes built in checksums and erasure coding, which allows us to detect them and fix them. ZFS also contains a lot of other built-in features like mirroring, snapshotting, compression, and dedupe that might be useful in the future. In particular, compression will become more far more important to the lab for our next generation of supercomputers. So here's a high-level diagram of what the lab's supercomputer architecture looks like. On the left-hand side of this diagram, we have a bunch of compute nodes which will be running scientific applications, and they will be pumping out tons and tons of data that is destined to land on the right-hand side of this diagram on Lustre, backed by hundreds of petabytes of hard drives. These hard drives in aggregate are able to ingest data at about 1.2 terabytes a second. However, despite how big that number is, it's not quite fast enough for what the lab needs. Scientific applications are intended to perform science, not perform I/O. So instead of writing directly to our lusters, hard drive back lusters, we instead land data on an intermediate stage called the burst buffer layer, which is about 10 petabytes or so of flash, which is able to ingest data at 3.2 terabytes a second, which is sufficient for our purposes. Once data is landed, the scientific applications are able to continue doing their science while the data is streamed out to the hard drives at a slower rate in parallel, thus allowing us to do more science. So for our next generation of supercomputers and their parallel file systems, the plan is to remove the burst buffer layer and have these scientific applications write directly to NVMe SSD enclosures that, as shown in the big circle on the right-hand side. So due to the economics of flash, we simply can't buy nearly as much flash as we can hard drives. So the total capacity of these enclosures will be somewhat smaller than what we currently have. In addition to less space, these flash enclosures will not be dedicated to writing data for supercomputers to write data to. Instead, they will also be shared amongst others file system storage stacks for various purposes, reducing the amount of data that scientific applications have available to them further. Additionally, for our next generation of supercomputers, we don't expect the scientific applications to write any less data. If anything, they'll write the same amount of data or even more, meaning we're trying to fit even more data on less space. So for our next generation of supercomputers, we will have to use compression. There's no doubt about it. So for the first step of this project, Brian Atkinson, sitting somewhere over there, benchmarked what happens when we move ZFS to NVMe. He benchmarked 12 drives backing Z pools in various configurations. So in this graph, there are two sets of 3 lines. The top 3 with the dots and dashes represent the maximum theoretical achievable bandwidth or write bandwidth for these drives. So there are 3 separate lines because as you add erasure coding, the total achievable performance drops. However, as you can see from this graph, the bottom 3 lines, the colored lines, are nowhere close to the theoretical maximums that are achievable. Instead, we're missing somewhere between 1/3 and 1/2 wall performance that these NVMe SSDs are able to write back, which is not good. We're not going to buy drives just to get half of the performance. We want as much performance as we can get. So as it turns out, this issue is caused by a series of mem copies and other memory bandwidth consuming operations that result in these performance lines. So there is a pull request that will fix this issue that Brian's opened called Direct.io. I encourage you to look at that. But for my project, I will unfortunately not be using Direct.io. I will be using stock ZFS. So the numbers in the future graphs will be limited to the solid color lines. And in particular, the next graph will zoom into the RAID Z2 line on this graph. where our maximum achievable bandwidth is about 12 gigabytes a second. So here's that graph. Once again, the maximum achievable performance of a RAID Z2 Z pool with NVMe, that's backed by NVMe, is about 12 gigabytes a second or so. And with that line, we further added more ZFS features that we wanted. So the first thing we added was checksumming, which, as you can see, caused basically no performance loss, which is great. We added a full-blown operation to our pipeline stage, and we basically lost nothing. The next thing we need to enable is checksum, or sorry, compression, because as I mentioned earlier, we're losing capacity, but writing the same amount of data or more. And the first compression algorithm we tested was LZ4, which is known to be a pretty fast compression algorithm. And it's also the default compression that ZFS uses when you simply turn compression on. And with LZ4, we lose about 70% of performance, which isn't too bad. Compression as in general is a pretty heavyweight operation, but we only lose less than 20%, which is great. However, as it turns out, lab data does not compress sufficiently with LZ4. Lab data is incredibly dense with high entropy, and the algorithm we need to use is gzip, which is known to be quite a bit slower than LZ4. And how slow is it? Well, it turns out when we enable gzip in Z pools backed by NVMe SSDs, our performance just tanks. It goes down to 600 or 700 megabytes a second, as shown by that blue line, which is unacceptable. We can't deploy Z pools with 12 drivers and getting only 600 or 700 megabytes a second. That's crazy. So what can we do about this? The path that we went down was to use computational storage, which is a relatively newish technology that's been developed over the past few years. So basically what we want to do is move operations that are computationally expensive to somewhere else off the host so that we can leave those resources for whatever operations that we actually want to do, like scientific computations. Computational storage can be implemented in a variety of ways, such as with FPGAs, DPUs, computational storage devices, computational storage processors. Some of you might be familiar with the NVIDIA BlueField 2 DPU. The hardware we chose to use was Idetacom's no-load computational storage processor, as shown on the left-hand side. So let me address the QAT-shaped elephant in the room. Doesn't ZFS already support offloading? Yes, it does. But first, QATs mainly are used on Intel machines, as QATs are Intel products. If you want to use a QAT on an AMD machine, you have to buy extra hardware. Second, if you want to use a QAT with ZFS, you have to further reconfigure ZFS and then link it into ZFS, link the QAT libraries into ZFS, which, as I've been informed by someone in this community, is a no-go. Additionally, when operations are offloaded to QATs, each operation is offloaded independently of each other. So let's say we wanted to enable encryption. So the data first needs to be moved to the QAT, encrypted, and then the result brought back into memory, aka 2 data movements for a single IO. Let's say you want to enable more operations, for example, compression. You take the encrypted data, copy it off out of memory into the QAT, and then bring it back into host memory. Another 2 data movements. And if you want to add checksuming, you have to copy the encrypted compressed data out of memory into the QAT, and then bring back at least the checksum, possibly even the original source data. So basically, there's a lot of data movement for a single IO, which we found to be a bit excessive. So as it turns out, a while back, Intel updated the QAT API to enable this thing they call chaining, which basically allows you to do one data movement and multiple operations in one go. But until those updates are implemented inside ZFS, they're sort of not useful to the ZFS community. So yeah, we can't use them right now. And as you might know, merging things upstream into ZFS might take a while. So even if someone does work on it, it still take a while to get in. So that's just with the QAT. So what happens if you don't want to use a QAT? What if you're developing your own custom hardware? What if you're a researcher who wants to implement something and run it in a real world setting with ZFS? Well, currently you can't, just simply can't. There's no infrastructure for adding new accelerators to ZFS. You have to either make your modifications and then push and try to get them merged into the main, merged upstream, which is unlikely to happen as you're probably the only person who has access to that hardware. So why would anyone else use your code? Or you have to maintain your own fork of ZFS and then keep it up to date, which is also quite frankly painful. So that's where we come in with the ZFS interface for accelerators and the data processing unit services module and associated providers. So at a high level, this is what using ZFS with our change set looks like. So here we have a simple diagram of a single node with data coming in from user space on the left-hand side. So with ZIA, with ZFS with the ZIA modifications, the user data will be passed forwards to this entity in the middle called the DPUSM, which is sort of like a multiplexer bus type thing that allows you to access accelerators via a standardized API. The data is then forwarded to providers to translate commands into the accelerator specific operations, which eventually lands the data on the accelerators and eventually onto the backend stores. You can have multiple providers going at the same time. Maybe you have a blue field here, a GPU there. You can have multiple providers for a single hardware device. It's however you want to implement providers is up to you. So now let's go a little bit deeper into ZFS. So at a high level, the ZFS write pipeline looks something like this. Data comes in from the ZFS POSIX layer, goes into the data management unit, and lands in the ARC. At some point, the data is flushed out of the ARC, is processed in the ZIO pipeline, goes through the VDEV layer, and eventually lands on the backend storage. And inside the ZIO layer, there are a bunch of transformations that can occur. The transformations that the lab is interested in are compression, checksumming, RAID-Z, and IO issue. So this is what ZFS looks like with ZIA. So what we do is shunt data out of ZFS into a different memory space, well, specifically accelerator memory via the DPUSM and providers. There were also some minor modifications to the VDEV layer, but those are implementation details and I won't go into them here. But basically data is just shunted out, never comes back into host memory and eventually lands on the backend drives. So let's first look at the data processing unit services module, or the DPSM. It's a simple kernel module, standalone, and the main purpose for it is to provide two header files, which provide standardized APIs for using computation storage. It provides a user API header and a provider API header. It also acts as a simple registry to keep track of what accelerators are available with which features and exposes them to users, say ZFS. Providers are also kernel modules, and their main purpose is to translate between accelerator APIs and the DPUSM's API. They declare what the accelerator provides. So a provider might declare every single functionality in your hardware, or they might declare some subset that you want to expose to your user. That depends on who implements it and how and what they want. We expect that, so providers should generally be implemented by accelerator vendors as they are most familiar with their accelerators. But if they chose to release their APIs for public consumption, we expect that individuals might want to only expose subsets of accelerator capabilities for whatever purposes they're using the accelerators for. A quick note, providers do not know anything about the users. So in our case, the user is ZFS, but providers should not know anything about ZIOs or ABDs or any ZFS structure. Providers are only there to offload blobs of data. It has no idea what's going on. So implementing providers should be decently easy. All you have to do is include two header files, your accelerator's header file and the DPSM's provider API header file. And with those two, you can define functions that are used to fill in a function structure that the DPSM declares or defines. And you can think of it as analogous to the VFS functions pointer structure. So with that structure, all you have to do is register your provider with the DPSM to let the world know that, hey, this provider exposes these features on this accelerator. And the primary purpose of a provider is to do three things. It provides opaque handles to accelerator memory that allows for users to move data to the accelerator, which then can be used to perform operations on the accelerator. Note that communication with your accelerator is communication protocol agnostic, which we'll get into later. But basically, if you have direct attached drives, you can use operations or function calls that communicate with direct attached drives. If they're not direct attached, you can use function calls that communicate with non-direct attached drives. On the flip side, using a provider as a user is pretty simple as well. All you have to do is include the DPSM's user API, find the provider you want, and then use the functions that the DPSM gives to you. And just as before, using a provider is just getting a reference to accelerator memory, moving your data to the accelerator, and then calling whatever accelerator function you want with your handle. So here is the crux of, or the core of the changes we made to ZFS, the ZFS interface for accelerators, which is a series of modifications to the ZFS write pipeline. It allows for transparent acceleration of CPU memory intensive operations with accelerators. So the main things we offloaded were compression, checksumming, grade Z, and IO issuing. We also implemented or offloaded decompression because it was kind of low-hanging fruit and it just worked. It was pretty simple. So with ZIA data, user data access is not modified, is not affected in any way that. So if they were writing to their files with some function, they will continue to write to their files with some function. After their data has landed and they want to read it back, they read it back just as they were before without ZIA. If they notice any changes whatsoever, it should be that ZIA accelerated their writes. So their IO just completed much faster than before. So ZFS administrators will notice some small changes. Specifically, right now we need to reconfigure ZFS to use ZIA, but the expectation is that when ZFS is merged upstream, or ZIA is merged upstream, we'll get rid of that requirement. Afterwards, once ZFS has been reconfigured, the administrator will have to select a provider for their Z pool, and then select which stages of their zpool are offloaded with zpool set ZIA, say compression equals on, which should be pretty simple compared to what all the other configuration options they have to set currently. So earlier I showed you this diagram with the ZIO pipeline stages that the lab wants. So once again, we want compression, checksumming, rate Z, and IO issuing to the backend drive. So this is the effect of what ZIA does to the pipeline. So just as before, data comes in through the ARC, it hits the first stage, compression, and ZIA detects one, compression offloading is enabled, and two, the data has not been offloaded. So the first thing that happens is the data is offloaded, represented by that big green down arrow. And then the compression stage calls the accelerators function, which runs compression, but faster than the software version, and simply returns a status code, which we usually expect to be just okay. The compressed data itself stays in the accelerator. Then ZFS the ZIO will proceed to the next pipeline stage, which is in this case checksumming, where ZIA will detect that one, checksuming is offloaded, and two, the data is already offloaded. So let's just not offload the data again. Let's just use what's already sitting there and compute the checksum. And the same thing happens with rate Z and this issuing IO, eventually causing the data to be landed on the backend drives, having never brought the data back into memory. So note that while this is the set of pipeline stages that the lab will be using, we do not require these stages to be used with ZIA. We've made it so that if you say wanted to turn off checksum, you can, and you can simply have compression go straight into rate Z, and the compressed data will simply be processed through rate Z on the accelerator, never having come back. If you wanted to do something weird, for example, enable checksumming, but not enable offloaded checksumming, you can also do that. When the compressed data hits the checksum stage, it will be brought back into memory, checksummed, and then returned to the accelerator in the rate Z stage. So obviously that causes thrashing, but we don't expect that to be your normal mode of operation. So we simply provide the primitives to do it, but we don't tell you how to do it or what you need to do. And if errors are experienced for whatever reason, say you ask for an algorithm that's not supported by your accelerator, but a previous stage did offload the data will be brought back into memory and processed in software. If for whatever reason your data can't be brought back into memory, say with a hardware failure, the entire write pipeline is restarted for that ZIO. This is possible due to the copy of the data that's still of the original data that's available in ZFS via ZIO transforms. So you might be wondering how fast or how much ZIA can improve performance. Before I get to that, here is a high-level diagram of how we plan to deploy ZFS with ZIA. So just as before, the host is on the left-hand side where ZFS runs. Data will come in through ZFS and ZIA, get passed to the DPUSM and the provider. And instead of writing to direct attached drives, we plan on writing to drives that are over a network, exposed through NVMe over fabrics. So what we want to do, what the plan is to write to our custom designed enclosures, which call accelerated boxes of flash, which contain NVMe SSDs along with accelerators, and just write to them. So unfortunately, because this was a custom design enclosure, we did not have them ready in time when we collected the numbers. So instead, we developed and benchmarked on a simulation of this, where instead of the enclosure, we simply had two standard servers connected to each other via NVMe over fabrics. Yeah. And this is what we got. So this graph is similar to the one shown earlier. So once again, our maximum performance achievable is about 12 gigabytes a second. And when we enable gzip, performance dropped to 6 or 7 megabytes a second. With ZIA and offloading all of the operations to an accelerator, we achieved that the numbers that we got on that black line, which is about 11 gigabytes a second or so, which is great. We got a 16x speed up. But not only did we move the gzip line upwards, we moved it upwards past LZ4. So we're performing better than LZ4 and compressing better than LZ4, allowing us to use our storage systems better in 2 separate dimensions. So in addition to offloading the write pipeline, we also offloaded the RAID-Z resolver pipeline. So for those who don't know, RAID-Z is basically comprised of 3 stages in the ZIO pipeline: IO start, IO done, and issue IO. So IO start is the read part, so we didn't touch that. Issue IO is the same as the issue IO stage in the write pipeline, so we just reuse that code. The core of resolver or RAID-Z resolver is done in the IO done stage, where there's a series of steps that are done to attempt to reconstruct data. And if the first attempt fails, try different combinations of the columns until you successfully reconstruct the data. So all of this was mirrored in ZIA to allow for data to be offloaded and the resolver operation as a whole accelerated. Unfortunately, at the moment, I don't have numbers for you, but this does exist, so feel free to play with it. So I would like to point out 2 very important points about ZIA. So first, ZIA does not provide a new set of algorithms. Gzip is gzip is gzip. We are not adding a new enum to say accelerated gzip versus normal software gzip. We did this intentionally because we wanted to make sure that if for whatever reason your accelerator goes away and is not available, we can still read the data off of your drives. Right. And secondly, the existing software implementations of these pipeline stages should not be moved out of ZFS into a software provider, because we need a way to default to an implementation, which is the software implementation. So that there are several arguments for and against moving the code to somewhere else, to a software provider. Before now, the current design is to not move the code. So having said that, of course, we have a software provider, so because the software provider is an exemplar implementation of the provider and not the actual operation, such as RAID-Z, we link back into ZFS to get the actual functionality, which real providers should just never do. So this provider offloads data to somewhere outside of ZFS, but it's still, of course, RAM, since there's no hardware involved. But the point is that it works. And this provider allows for testing and validation of ZIA, which should be useful for CI builds and whatnot. Additionally, recently, the QAT code has been moved into a separate provider, allowing for ZFS to not need reconfiguring or linking with the QAT code. So because the main ZIO pipeline stages that the lab wants are compression and checksumming, the encryption stuff was dropped for now. But if someone would like to take on that part, would happily accept pull requests. And the QAT provider is currently untested, but it does exist. So if anyone wants to play with it, feel free to go to that link and download that branch. So there are a bunch of future directions we could go down. So for example, we could implement more offloads, or such as the entire read pipeline or D-rate resolver, or enable asynchronous offloads, similar to Intel's QAT training, because right now ZIA is sort of in lockstep with the ZFS pipeline. The control flow is controlled by ZFS, while the data sort of just sits there waiting for the next operation to be offloaded. But for the moment, the main goal is to try to get ZIA upstreamed as soon as possible. And to do that, I need help from the community. Could use more reviews and comments on the PR, could use more testing, could use some help with the build system stuff. If you want to look at the code, there's a pull request open on the ZFS repository. Additionally, the DPSM can also be found on GitHub. And if earlier I mentioned that there were issues with too much bandwidth being consumed by ZFS, currently reducing the achievable throughput when using ZFS with NVMe SSDs. The pull request to fix that can be found here under the direct IO pull request. Cool. So before I get to questions, note that at the end of these slides, or rather, after this slide, there are a series of slides that basically provide a quick demo of how to use ZIA with the DPSM. So if you want to play with that, feel free to play with that. And with that, any questions? I think I saw you first.
Okay. Yeah, quick question is, so one that sort of problems with offloading accelerators is that if your accelerator is meaning it doesn't match what you can do back in data, they can actually become a bottleneck in hardware acceleration to keep up with the actual amount of data going through.
Sure.
Do you have any ideas or methods to be able to say, all right, well, we can't put everything to the accelerator, we have to put some data to an old pipeline in order to maintain our data stream, because actually that data accelerator itself has become a bottleneck?
At the moment, we don't. But we have thought about it, but we don't have any solution at the moment.
One more follow-up question, or not follow-up question, but a separate question. You mentioned D-Ray Silver as a possible extension. Does that mean you actually have D-Ray rights as existing in your current code, where you can just if you write new D-Ray without do with it, non-resilvering? Is that supported right now? Or
No,
just racing?
Someone.
So, yeah, so I saw you did an easy benchmarking, right? It's like 10 times speed up.
Just standard write pipeline.
Okay. So have you done any like other algorithm like RJ4 on STD, ZSTD, and
good question. So when we started this project, ZSTD hadn't been integrated into ZFS yet, so we just didn't use Z standard. And we also, our hardware supports only accelerated gzip, so we sort of couldn't test accelerated Z standard.
The QAT provider that you have, is that using the new version of QAT or the older one?
The older one. I just moved the code out. I'm not a QAT expert.
You mentioned direct IO patch in this context. Does it mean that we are practically dropping arc out of the patch completely, or it's just dropping drops from compressed arc to non-compressed arc, or what's the relation, particularly if you write? I guess we never see compressed data in memory at all. Compressed, are we expected to cache still an arc, or you're just possibly copying directly to user space?
Could you just repeat that?
You mentioned direct IO patch
Right.
in your at the
Right.
end of the slides. So do you expect it to be preferable way of using ZIO without caching data in ARC?
Oh, okay. So no, we don't have a preference. It should work for both.
But compressed data never appears in memory.
Yes.
ARC can be only uncompressed or no ARC at all.
At the moment, I believe we disable our compression.
I think to kind of follow up on that, is there a way to get the compressed data from the accelerator into the ARC? Have you guys looked at that?
Not directly. So obviously we have ways to bring data back into memory in case of accelerator failure, but we don't explicitly do it for the ARC.
So you mentioned that the card is driven forward by the ZIO pipeline,
right?
And the data kind of sits on the card. So if ZFS is too slow there, is there a limit to how much data the card can have in its flight?
No, that would be a accelerator specific detail, implementation detail.
And for gzip, do you know, well, gzip is gzip. It turns out it's not always the same. Do you know if it uses the same starting table as the Linux kernel module, or if it uses something more like QAT, which is a different table, so the same block won't compress to the same checksum as the software implementation?
Right. So the idea is that we want the same bits to land no matter if you're using software or hardware. But yes, our hardware actually wrote slightly different bits, but because we computed the checksum on those different bits, it was fine.
Maybe one last question then. Since the accelerator handles actually send the data to the NVMe at the end, how does the interaction with the VDEV layer go to figure out where to put the data on the NVMe?
Right. So we also have some hooks inside the VDEV layer to keep track of stuff inside ZIA. But so the data doesn't go to the NVMe. That doesn't land on the NVMe's after, like, across the network. It first the accelerators are also across the network. So, right, it's not like a separate thing. They're sort of right next to each other.
Right, it's the accelerator that actually issues the write to the NVMe, not ZFS.
Yes. Well, so ZFS does the ZIA call, which tells the accelerator to offload it.
Great, thank you very much, Jason. So we'll have a short break now, about 10 minutes, and we have one more short talk before lunch. Thanks, everyone. Yes.
So dark. 3 hours worth of stuff. Yeah.
Exactly.
Really?
All right, let's have a seat. We have a talk, one more talk. Lee Jung is going to be talking about ID map. Going through slides. The computer's a little slow, but it will work.
It's a new one, right?
This is you, right?
I sent you on October 13th.
Yeah, this is the
Friday.
yeah. This should be this is the new one that you sent me, right? Yeah. Cool. All right. So have a seat and oh, there we go. Great. Have a seat and welcome Yujun Yang from MathWorks.
Thank you. So I'm Yudong Yang. I work for a company called MathWorks. Today I'm going to talk about ID map mount support in OpenZFS and its application in our company. So it makes a big deal for our company, so that's why I'm here to talk about it. So a little bit about our company. I think many people know MATLAB, but not necessarily knows our company. Our company is called MathWorks, who created this MATLAB software. So we developed a mathematical computing software, MATLAB and Simulink. So around the world, we have like 5 million users in 180 countries, almost all over the countries. Wow. In the country, in the world, probably 190 countries, I think. So approximately 100,000 business, governments, and university use our software. So it's it's a very popular software in the academic area, especially also in the industry, you know. So a little bit background and motivation about this this work. So I work for the company in a group that support the product development. We basically design, implement, and maintain the infrastructure for the product development. We have hundreds of servers worldwide. The main file system we use is ZFS. Previously, we use Lumos, you know, and then we migrate to Linux for some reason. So in the CI system, there is a single raw account which own all the files and the folders. That's the nature of our CI system. So basically, in the system, CI system, we have a build area. You know, that area is huge. It's like 12 million files, 4 million folders, right? So each developer, they're going to work in a sandbox. Basically, when the CI system finishes, you get something ready. So developer can develop on top of this sandbox, right? So basically, we use a ZFS. It's a fantastic clone technology. You know, the clone can happen instantly. Basically, the developer get a sandbox. But the problem is the sandbox creation takes long time. We know the ZFS cloning is fast, but after that, we have to do something to make this sandbox ready for a developer. So here's a typical workflow. So on top of that, we have an origin, the ZFS dataset, and its snapshot, right? So this one has 12 million files, 4 million folders. And the clone for each developer, we clone from this origin. Each developer get a clone sandbox, right? And then after that, we have to change the ownership to the developer from the lower account to the developer. That clone process, it's not a big deal if you only have hundreds or thousands of files. But now you have to clone millions of files. So that's a challenge I have been facing for years, right? So, so here's the pain point. Basically, the clone, it's a bottleneck. Why? It's because the trade is huge. We have to clone from the lower account to the developer UID basically. That's the only thing need to be done. After you change ownership to developer, the developer can start to work. So for this clone, it's time consuming. It takes extra space because the ZFS copy on write, I think. And also it uses not so memory. Not so memory. So here's a typical sample resource consumption. We run this on an idle test server, which has like a 1 terabyte of memory. We run 3 times. Yeah, it's an idle server. It takes like 3 minutes for this to finish. Memory, delta memory, you basically used after minus used before. Memory, like it takes like 70 gig. A huge amount of memory for this clone to happen. Also the disk space, you know, compared to the original sandbox size, 766 gig. Not many, but you know, we have so many developers. We have to do this so many times on a server. That's a big deal, all right? So actually, you may ask, do you do the like parallel tuning? Yes, we do. Even with the parallel tuning, it's still slow. On a typical production server, it takes like 10 minutes, 20 minutes. Sometimes if the server is busy, 30 minutes. So basically, the developer want to start to work, they have to wait like a half an hour. All right, so that's basically the kind of challenge you have been facing for many years. I joined this company in 10 years ago. So we have been facing this problem for almost 10 years. There are other groups who come up with some different approach, try to speed up this developer process, you know, but doesn't help much. So, so we have been asking this question many times. So why do we have to do this clone? Is there any possibility we can just not doing this clone, you know? Right? So the first thing we think about it, can we impersonate this raw account ID? No. Impersonate the developer ID as a raw account ID. We cannot do that because of the security reason, right? It's very simple. So next is it possible so that this raw account ID can be magically mapped to this developer ID, right? This can magically happen. Why do you have to do this clone, you know? So yeah, so we found this Linux feature which is called ID mapping. It's a fantastic feature introduced in the Linux kernel in the VFS layer, basically. So this is a kind of timeline. So in April of 2021, this ID map feature was available in Linux in kernel 5.12, done by a Linux developer, Christian, I think. And then, even before this April 2021, I think probably because of the release critical kind of 5.12 release, somebody in OpenZFS already did some work so that OpenZFS can be compiled. So there's some preliminary work has already been done. But it's not plugged in to use this ID map. It's just so you can compare, you know. So in December 2021, somebody filed a feature request, which is requesting this ID map feature in OpenZFS. I saw that feature request. Oh, I said, this is nice. So we should do it, you know. It works perfectly for our company. So we started working. Well, not really. We wait for some time. We hope somebody will do the work. But you know, it's been quiet for a few months, and then probably in March 2022, we started working on it. And in June, it's ready to be used in MathWorks. We tested. It just works perfectly for our use case. So this is a basic idea. In the developer, the Linux developer language, this ID mapping basically it changes ownership in a temporary and localized way, so that you have a ID translation, right, from the ZFS layer to the namespace in the like ZFS storage space. So this translation automatically happens. So that's basically the way how the ID map works. So in our use case, we try to map the raw account ID to the developer UID in each data set in a Chrome the sandbox data set. Right? So now you don't have to do the churn. The file still will magically appear to be owned by the developer once you have the ID mapping. But so that after this happens, right, the developer can make changes and create new files. But on the disk in ZFS, the UID or owner ID, it's still the raw account ID. So that's basically what happens here. So looking at that same workflow graph, right? So the clone still happen instantaneously. And then after that, for each sandbox, we set an ID map on the data set. And then we remount this data set using the provided ID map information. And then after that, everything just works. Well, once you have the ID mapping, when you do the file operation or you get attributes, that kind of thing, there's some kind of translation happen, but that translation very fast. So next, I'm going to talk about the updates I have done to the ID map mount feature. I've gone through 3 basic iterations. So first is the status of ID map as of 2021. So it's ready in 5.12 kernel. And then at that time, it's available in ext4, XFS, and some other file system, but no NFS server support. So no OpenZFS ZFS support. Looking at the graph at the right side. On top of that, it's NFS server, right? NFS server, you call the VFS layer, and the VFS layer will call the file system driver layer. So the work is done in the VFS layer and also some file system driver layer. like ESD4, XFS. So the work for us, we have to do ZFS, NFS. For SMB Windows access, no need to do anything. Because the SMB or some person like SMBD see the file system as if the developer is sitting on the server, see the file system. So the first one is a basic support. This one basically, it doesn't work for container. The reason that in the container case, there's something missing in the kernel implementation. You have a namespace, file system namespace attached to the superblock, but it's not being used. So basically, this one, there's no kernel support, or no container support. If the container uses a different non-default user namespace, right? But it works perfectly for our company, for our use case. There's an example of the ID mapping. So suppose we have a mapping basically 0, 1 million, 1 million. What does this mean? Means you map the ID in namespace, ZFS namespace, let's call it ZFS namespace, mapping the ID from 0 to 999,999. So 1 million IDs. You map those 1 million IDs to another 1 million IDs, starting from 1 million to 2 million minus 1. That's so you map the ID in the ZFS space to the VFS layer, which is it's kind of a user space. You can think that as a user space. So for example, if the UID in the ZFS is 110, right? 1,100, and then the ID in the VFS will be 1 million, 1,000, 1,100. Right? So I think you get the idea how this mapping works. So the kind of change I made to the ZFS, just take 2 examples. The inode operation, right? First is a create. So in the new kernel, the inode operation defined to take the mount namespace as a first argument. So basically for each create operation, you have the ID mapping as an input. So now with that ID map input, you can do your translation. So typically what we do is here, first we have the credential. We get the current credential using current dash, right? And then in that credential, you have the UID, developer UID basically. And then you can translate the developer UID to the UID using the ID map to the ID which will be used in the ZFS. Yeah. Also other bunch of stuff like other like a maker, semi-link, bunch of stuff. And then the other way around, right? From ZFS to the username, it's like a get adder. Also, you have this the first argument as the ID map provided to this function, and then in this implementation, we just use a generic fair adder, that function, which is available from Linux. Yeah, it will make it to the work. So next change is about the support container. So our company is considering moving towards containerize our storage service. So basically, yes, that's why we did this work. But on the other hand, we also need to, make this ID map feature works for any use case, right? So that's why we did this work. The basic idea is basically take advantage of the new kernel function which does this translation. So now instead of only have one ID map, now you have two ID maps to take care of. You have an MID map attached to the super block. You have another ID map for the mount point. So to use this feature, there's one for the namespace delegation, I think. You need this to use this ID map in a container. You want to map in a container. You dedicate the data set to the container, right? So kind of typical change, we've done this. We introduced two functions, basically. One is convert the ZFS UID in the ZFS 9 to the VFS UID. There are also GID to VFS GID for sure, right? So this function takes three inputs. One is a mount ID map. Another is the file system namespace, the ID map. Right? So you have input as a UID from the user ZFS space. So another one is the other way around, So you may wondering what this file system user namespace is from. It's from the inode. Inode has a super block, and then in a super block there is a user namespace. So here's an example with two ID maps. So here basically, you can think there are three namespaces. One is a ZFS in the host. Another is a container namespace. And then you have this VFS kind of what the user is saying, kind of namespace. So that kind of translation happens when we do all the ZFS operation. Either you get data from ZFS or you write data to ZFS. I don't want to get into this. Maybe go through this. So the first ID map, FS user namespace, right? You have a map from 100K, 0 to 100K minus 1. Then map that to 100K all the way to 200K minus 1. Right? So the second is on the mount point, the actual ID map on the mount point. So that happened for the UID from 0 to 10K minus 1. And then map that to 10K to 200K minus 1, 20K minus 1. Right? So this mapping, if you look at in the middle, so it's part of the file system user namespace. Right? So the last one I did is about the support the 6.3 kernel. So Linux did something. So they basically consolidated their ID map stuff, introduced a type def, which is hidden. Nobody can say it's failed. It's hidden type def. And then the GPL almost all the symbols. Yeah, like the default ID map, it's a GPL symbol, and also the conversion, those critical conversion API, they are also GPL. But the logic is very simple. You just do a translation, right? One to another, and use the second map to the translation. That's all happens in those conversion API, but they made it GPL. We don't want to get into this kind of GPL stuff. So what I did is basically, it's already written in the previous iteration. We did this, it's almost the same thing. The only thing did is use a new type def, right? So we have already done that, and now we do it in a new type def. So basically, we define our ZID map type definition, which is basically same as a mount ID map type structure, which is hidden. But to use a hidden structure, there's no way to use a hidden structure. So we define this mount ID map structure in our header file. It's no big deal. Just two fields, two fields. So for the new kernel, we define this. For the old one, we still define as a user namespace structure. Right. So it's almost like the same translation function. You take the first one as a mount ID map, and second one as a file system user namespace. Right. So that's all we did. But in this one, this iteration, there are many changes. We have to take care of all the kernel. There are many if else, kind of thing to work around the to support all the kernel versions. Yeah, it's lots of changes. But recently, a few days ago, I tested this in the 6.6 kernel, I think. There's some funky stuff. So we may have additional work to do. Yeah, basically we are basically fighting with the Linux kernel. They keep changing things, and we have to keep up. So what's next? You may ask, people say how to use this ID map, right? I didn't talk about this, how to use it. To use it, you have to mount it. Mount with provide the ID map information. That mount doesn't happen magically. So we internally, we did this work, which works perfectly for our use case. So in our use case, we basically, at the dataset creation time, we provide this ID map information. Then we remount with the provided ID map information. So basically, what we do is on the existing mount point, which is mounted by ZFS, we set a mount attribute, which is called ID map mount attribute. Provide the ID map information as a file display input to whatever the sys call. And then after that, unmount it, and then move the mount point. That's all need to be done to mount this data set with the provided ID map information. So what we didn't take care of is a case of like the following scenario. If somebody changed the ID map from something to else, right? Something else, you have to redo this kind of work. We didn't do that. It's not our use case. But to upstream this change, we have to think about this kind of scenario. So in case of change the ID map, what need to be done? You have to do unmount twice, basically. So first, you already have the ID mapped mount. So that one, you cannot simply change the ID map information from one to another. You have to unmount it, remount it with no ID map information, and then set the mount as a new ID map file descriptor as a mount attribute, and unmount it and move the mount point. I'm still working on try to simplify this, but yeah, still working in progress. But I mean, this kind of thing, I'm not sure if it can be done as a hackathon tomorrow. Tomorrow I'm not here, so it's welcome to do that. So all kind of the kind of logic is already available in a test utility, you know. It's called ID map util.c. So in Linux, the mount utility also added a new option called x-mount.idmap. With that option, you can mount the dataset with the provided ID map information. What I did is basically similar thing, but I think in the ZFS, code we have two options, right? Either we use a mount utility or we use a mount syscall. We have two options. Typically, we use a mount syscall, I think. So I don't think it's a good idea to use this X-mount ID map kind of option available in the mount utility. So what we did, we introduced a user namespace, a user property called something ID map, you know, column ID map. And so for this to be introduced into OpenZFS, I'm not sure if it should be the user property or system property. I haven't done this testing. If it's a system property, you have to think about the old version, new version, you know. I don't know what happens, but anyway, it's up for research, you know. So, how can I help? I think that not many companies are using this ID map thing. It'd be nice, so you can try this, you know, try this in your use case, so that we can maybe identify some edge cases. In the DFS code, there are so many places doing the ID kind of stuff. We may have missed something, you know, who knows? So that's one request to the community. Second is this NFS support. We have an internal version basically to support this NFS server use case, because our client accesses the NFS versions through the NFS protocol or SNB protocol, either from Windows or from Linux or Mac. So we have to do that. We had to do that work to support the NFS, but there's some challenge to upstream this this change because of the kind of licensing issue. You know, we don't want to get into that kind of trouble. So maybe somebody can help, you know. Any questions? Thank you.
One question.
remapping like a whole range, similar to like Samba's auto rate mode or something. It seemed like it wasn't per like individual user. Like we have user 1, 2, 3, 4. The next one was 4, 5, 6, 7. It seemed like it shifted the whole range. Or is the ID map actually providing a number on one side and a number on per user basis, the whole table that you insert?
Yeah, so in our use case, we only map one ID. Well, actually, two IDs. We map the user ID, the role content user ID, and another one is root user. Is some cases we need the root kind of access. If you don't do the root mapping, the root user will appear as an anonymous user. So we only do two mapping. But then after we roll out this feature in production, some people complain, I cannot write to a 777 file. Yeah, they complain because that user, he or she works in the sandbox which is owned by different user, and that user cannot make change to the 777 file. And well, to solve that problem, it's very simple. So mapping UI the door ID to the developer ID, right? And then for other ID, we do the identical mapping. That should solve the problem. Yeah, without ID mapping, so the user is not going to perform any work.
Thanks, Joe. All right, next up, lunch. I think, is Ala here? I think that the lunch is set up over there on the other side of the office. So enjoy, and we'll be back at, I think we have more than an hour for lunch, and then after lunch, I'll be giving a talk with Don. So, thanks.
That's right.
Yeah. All right, we'll be restarting in just a moment.
Do a lot of presentations or something. Yeah. Whatever, don't fix the sheet too. Not ZFS lately, but I might get ZFS stuff. Yeah, I did my dabble here and there. See kind of helps it go based on the project. We have some ZFS stuff. Yeah. Whatever.
All right, thank you. Welcome back. All right, next up, myself and Don. We're going to be talking about RAID Z expansion. I'm Matt Aarons. I work for Delphix, and my work on RAID Z expansion was sponsored by the FreeBSD Foundation.
I'm Don Brady. I'm with Clara, and also being sponsored by Systems for the RAID Z expansion.
Cool. All right. So has anyone had this problem or know someone who has this problem? You have a full pool. It's all used. You're using RAID Z. What do you do? Well, what you would like to do, your proposed solution is to add another disk and expand the pool's capacity. But until now, you haven't been able to do that because you have to add entire RAID Z groups at a time. So if you're like a big enterprise customer, you can roll in a new, $100,000 shelf, plug it in with 50 new drives, and you're all set. But if you're a home user, you would just want to go to the store and buy another like $200 drive and put it in there, which you can't do now. But our solution lets you do this. So now you can run zpool attach just one new drive to your RAID Z. It needs to copy all the data around to use the space in the new drive. And then when that's done, you have additional space available. So when it completes, then you'll have the new drive, which in this case is number 6 in your RAID Z group. It tells you about the expansion. Yeah, it took a long time to do it, but it's done now. And now you have more space available. In this case, 600 megabits available. Reminder that the space available is not the same as the space free according to zpool list. So the difference here is zpool list is telling you about how much actual bytes are allocated and free on the disks, versus ZFS list is telling you kind of how much space is available to you if you were to write it, ignoring compression, but taking into account parity, for example. So the key thing here is that the ZFS list is like pretending that you don't have to pay for the parity. We've already kind of taken that into account versus zpool list. It includes the space, like the free space includes space that is going to be used by parity. All right, so I guess that could be the end of the talk. Like, it works, yay! But that would be a very short talk, so I thought I'd tell you guys a little bit about how it works under the covers. And maybe along the way, you might come to understand why it took 6 years for me to do this. Most of it's because I wasn't working on it the whole time. But, what we want to think about is what does the state of the disks look like? So it's useful as a point of comparison to think about what does it look like for a traditional RAID, right? This might, if you don't know the internals of RAID Z, you might be thinking this is how it works. This is how it works with like traditional RAID 4, 5, 6, etc. You have, in this example, 4 disks. The last disk has all the parity. It's the parity of the other 3. RAID 5, it just kind of puts it diagonally across, but conceptually it's the same. So if you were to add another disk, what we need to do is just recalculate all the parity and reflow the data. So, we reflow it sort of like a word processor. You make your margins smaller, and now the words flow to the previous lines, just like this. So in this case, like in this sector 4 got moved to the previous row, the first row there, and then we have to recalculate the parity because now we need the parity of sectors 1, 2, 3, 4 versus before we just had the parity of sectors 1, 2, 3. Relatively straightforward. Obviously, you have to recalculate the parity, which has some cost, but you have to read all the old data and rate it all again to different locations. And we have to do the same thing with RAID Z. Like we have to move all the data around, but the way that we handle the parity is very different because the way that RAID Z handles the parity is very different. So with RAID Z, as I alluded to before, the parity is included in the allocation. So kind of more layers of ZFS know about that parity. And so what we're doing with RAID Z is we're moving all of the sectors, including the data and the parity. So the parity doesn't get recalculated, it gets moved to a new location. So in this case, like sector 5 is the parity of 6, 7, and 8. And we're moving it to a new location on the new disk, but we still have sector 5 being the parity of 6, 7, and 8. So the cool thing about RAID Z is that with RAID Z, from the allocation point of view, the parity might be like in lots of different places. It's not just all on one disk, or kind of by math, we know that it's on this disk and then that disk and that disk and that disk. It could be in all different places depending on the sizes of the blocks after compression, the sizes of the blocks as they're written. So like in this example, we have 5 and 6 are one logical block, and then 7, 8, 9, 10 are one logical block. So it's kind of a degenerate case where block 5 or sector 5 is the parity of just 6. It's not a full row of parity, it's just a partial row of parity. But the good thing for reflow, for RAID Z expansion, is that when we reflow it, we don't care where the parity is. We're just moving it around as though it were any other sector. And we don't need to copy the allocated space, right? ZFS knows what space is allocated in freed, so we don't need to copy any space that is not actually allocated. Obviously, the typical use case, practically all the space is allocated, so this isn't like a big performance win. There are probably some other use cases that you might run into where like you accidentally configured it with 4 disks, you used it just a little bit, you meant to add this 5th disk that was there all along. You can use expansion for that, and it's going to be much, much faster. So the cool thing is, like, it works. You just read all the data sequentially, write it all sequentially. And because each logical stripe is independent, we don't need to care about where the parity is. And the key thing is that the segments are still on different disks. So the redundancy is preserved. I'll show you kind of how an example of this. So for example, if we think about the blocks 7, 8, 9, 10, you notice those are all part of one parity, like one group. 7 is the parity of 8, 9, 10. And they're all on different disks. And that means that if any one of those disks dies, then we still have 3 of the other pieces of that group 7, 8, 9, 10. And after moving it, that group 7, 8, 9, 10 is also on 4 different disks. So if any of those disks dies, we still have 3 of the pieces of it. And so we can reconstruct it. Additional cool thing about RAID Z expansion, once you've expanded it, you have all the free space, you have a bunch of free space at the bottom here. That's going to be, however much space was in the new disk is now free space. It's all kind of at the bottom. But in the space in the bottom or free space that happens to be in the middle, in this example, we can allocate the larger stripe width. So for example, in the block like 7, 8, 9, 10, you have 1 piece of parity and 3 pieces of data. So the ratio between data and parity is 3 to 1. But when we write new data, now we have 5 disks. So we can write 1 sector of parity into 11, and then 5 sectors of data, 12, 13, 14, 15, 16. So you have a better ratio of 5 pieces of data to 1 piece of parity. So basically your space efficiency is going to be better. But this brings up kind of a little bit of trickiness. So like that's great that we did this allocation and it's a bigger allocation, but when we go to read the data, how do we know whether it was written with this old layout with 1 parity to 3 data or the new with 1 parity to 4 pieces of data? The way that we do this is when we're reading, we need to know what was the logical stripe width. So the way that we do it is we say, okay, while we're in the middle of the expansion, we're still allocating, while you're in the middle of the expansion, you can still use the pool, right? You can still do reads and writes, everything's online, just as you would expect with ZFS. And we're still doing writes using the old width. But once the expansion completes, then we'll switch over to using the new width. So all writes, all allocations after that point are using the new width. And so we can use that kind of time point, that TXG, as the cutover time. So any blocks that were allocated before that cutover time are using the old 4 wide, and any blocks that are allocated with the new after that cutoff time are using the new 5 wide allocations. One kind of little wrinkle about this is that like I mentioned before, ZFS list, it tells you how much space how much logical space you could write. It's trying to tell you, it's making some assumptions about how much parity is going to be used in the future, and then predicting you're going to be able to write this much data, and don't worry, we have the space for the parities outside of that number. But when we change the data to parity ratio, we can't actually change the way that accounting works. So you're going to end up seeing a little bit less. It's going to say you only have 1 terabyte of available space, but actually you can write a little bit more than that because of the improved data to parity ratio. So we talked a bunch about the end state that this is going to be in, what does it look like at the end? We reflowed all the data. But how do we get from the beginning to the end? Obviously, we cannot read in everything from disk, keep it in memory, and then pop it all out in the new layout. Right, so this is an example. On the left, we have the initial state. On the right is the new end state. And each color here represents 1 parity group, where all the sectors of that color are one of them is the parity and the rest of them are the data. All right, so we're starting off here. Here's some possible intermediary state, right? We've reflowed some of the stuff, but not all the stuff. And these green sectors at the bottom, 29, 30, 31, 32, part of them have been moved and part of them, some of them have been moved and some of them have not. So what happens if one of the disks were to fail? Like if this fourth disk fails, then we'll have lost both sector 29 and 32. So that's a kind of a problem for us, because if this is RAID Z1, we can only lose one disk, which means we can only lose one piece of the data plus parity in that group. But in this case, we've lost two of them, right? 29 and 32. So we can't recalculate both of them from just a single parity. All right. So that would be problematic. And we really need this to work, right? Like during the expansion, this is not like don't just make sure nothing fails while this is in progress. No, that is not how ZFS works. It's all online. All the guarantees of RAID Z still exist, so you can still lose, P disks, where P is the number of parity. If you have RAID Z3, you can lose 3 disks while you're in the middle of the expansion, and without losing any data, everything is still preserved. So how do we do that, given the problem I just mentioned? So the trick is that the data is in 2 places at once. So the sectors 29, 30, 31, 32, if we've moved some but not all of those, then we make sure that we can still continue to read them from the old locations. So I'm going to move, hopefully the audio still keeps working, but we can, even though we moved this already, we can read it from the old location here, where only one of the pieces of data has been lost. And so we can do the reconstruction. Now, the trick is just, we have to make sure that that invariant is always true, that the data is still at the old locations and we haven't overwritten it. So to make sure that's true, there's 2 key things. One is we have to have not overwritten it yet. The other is, what exactly do we have to have not overwritten? Because I'm showing you these examples where there's only like 4 pieces of related data. There's the data 1, data 2, data 3, and parity. The parity is the parity of the other 3. But you can have like very large blocks, right? Like you can have a 16 megabyte block in ZFS. So does that mean that like the whole 16 megabytes can't be overwritten while I'm in the middle of this? Well, no. Thankfully, each stripe is processed independently. So even if you have a large block that's composed of many sectors and many stripes, so like you have a 16 megabyte block, you divide it into 4 kilobyte sectors, that's, I don't know, like a whole bunch, more than 4. But each like one sector wide piece of it can be considered independently. So even with the 16 megabyte block, the first 12 kilobytes of it still works as though the rest of the block wasn't there. So we can reconstruct that first 12 from the first 3 sectors plus the sector of parity without regard to what's in the rest of the block. So that means that we only have to keep a separation of one like width. So in this case, like 4 sectors, not the maximum block size of 16 megabytes. So that's great. But what about at the very beginning? So at the very beginning, I think I have an example of this, maybe not. At the very beginning, you have a problem where, well, the separation is only 1 because I added 1 disk and I have 1 free sector there, and I can only move 1 sector at a time. So I might end up having to overwrite within that same, even though it's only 4 sectors that I have to keep intact at a time, one of them still might be overwritten. So we have a special case that happens just at the very beginning of the expansion where we read a bunch of data, we put it into this reserved space that happens to have been reserved 20 years ago. We thought that we were going to use the first 4 megabytes of every disk as like a part of a bootloader region. And it turns out that like that was probably for some like ancient Spark bootloader that doesn't even exist anymore, was for some old format you know, it was this is invented like pre-GPT partitions. So probably had something to do with like some old Sun partitions. Thankfully, nobody ever used that space. So this whole time, nobody asterisk ever used that space. We were able to use it here. So basically we can copy the first 3.5 megabytes of each disk into this reserved region that's on each disk. And now the data is in two locations, this reserved region and the original location. And then we can overwrite the first beginning of the real locations with all the newly formatted reflow data. So this is showing kind of what happens there. We read the first, it has to be at least kind of the width squared. So in this case, like 5 times 5, it has to be at least 25 sectors total. But in practice, we have this much larger space, 3.5 megabytes. So we read the first 3.5 megabytes, and then we write it to this scratch space, and then we can overwrite the first 3.5 megabytes of each disk, and then atomically switch forward and say, okay, that's all done. Now we can move forward having sufficient separation between where we're reading and where we're writing, that we always have at least one stripe worth, and we're not overwriting ourselves. So once we've done that, here we have enough we have, you know, at least one row of basically unused space, sectors 21, 22, 23, 24, and we can start copying stuff. So we can move the first one. So we read sector 26, we write it to its new location, which is overwriting 21. Then 27 can move to its new location, 28, and so on. Cool. So some of the design implications of this. So it works with all kinds of RAID Zs, right? RAID Z 1, 2, 3. Each expansion happens kind of one at a time. So you really are adding one disk at a time, doing this whole reflow, and then that's done. But then you can add another one. So if you need to add a whole bunch of disks, well, maybe you should have been adding them as a new group. But if you didn't want to do that, or if maybe it's one this month and another one next year, you can do that. As I mentioned, the old data has the old data to parity ratio. The new data has a better data to parity ratio. And during the expansion, disks can fail. But if a disk fails, we're going to pause the expansion and wait for the pool to become healthy again. The problem is that if we were to continue the expansion, then we would both not be able to read from that dead disk, and we also wouldn't be able to write to it, which could result in like two blocks in the same stripe being lost. So we wait for the reconstruction to complete, and then the expansion will automatically continue. All right, fun demo times. Okay, good. I'm just going to make sure this comes up because the computer is a little slow. Maybe it's a lot slow. Do you want to talk about your work?
Okay, hopefully this is pulling it down from the.
Yeah. Let's give it some time.
All right, yeah, so this is the first time Matt has given this talk, I think 4 times. And this is the first time that actually we're gonna have a demo. And so here's the demo, actually working. I'm using 4 RAID Z 1 and then adding to it. You can see there's 4 disks. And then catch up to the. Okay, so yeah, so Matt mentioned that the space will come at the end. So this will be a good test of people's memory. We'll remember what this number is, 465. I will forget within a few minutes. 465 is how many metaslots we have right now. And so we're going to go and find the disk. In this case, it's SDF. And this is just showing you sort of the awkwardness of administrating a zpool create, because you don't want to use the SD names. You want to use a persistent name. So this is just finding the persistent name. Okay, there's my disk. So then here we go. the main attraction here, Z-pull attach. And then as a way of background, this system is like only 4 cores, 32 gigs, and these are pretty slow, like 2016-ish drives. So this is not necessarily the worst case because it has 4K sectors. 512K would be the worst case, but there we go. And then the estimate, a little shocking there, 1 day and 23 hours, 2 days. It doesn't take that long, but let's see. And then we'll go used as that scratch space. And so in the Uber block, we keep track of whether we're using it, where we are in the whole process, and then the offset. The offset is used to tell us where we last successfully sank out the disk. And so here we go. We should be seeing a little bit better, but 24, 25-ish megabytes per second is what this rate is, this array is capable of. And then for fun, you can see that bottom row, he's only taking writes. That's the new disk. And then you should see at some point, I yanked the disk out just for fun. There it is. All of a sudden that disk is taking no reads because he's not in the array. And then the expansion process will figure that out. And I think there's a status in here. So yeah, I'll do this equal status pause until you get that thing healthy again. And so we'll get it healthy again. And basically I just replaced it. I put the disk back in and it resilvered. And once the resilver finishes, then 15 hours later, it comes back and we have our new pull with, let's see, I'll show the status. It took exactly 15 hours, right, rounded up a little bit there. And you can see that now we have 9 terabytes available for allocations. And let's see, and then what was the number? Anybody remember that number? 465, good memories. You'll see here that we got 582. So basically it's appending that new space under the bottom of your VDEV. Okay.
Uh-oh. Playing it again. I tested doing the video, the recording, but not going to the next slide after that. So sorry.
Okay. I'm going to talk next about how we tested this. This is one of those big features. We want to make sure that we have adequate testing. And so first I wanted to do a shout out to VStack. They actually stepped up and did a lot of testing for us and provided hardware for their testing efforts. That was nice to have that resource available. So for the test suite, we want to make sure we cover all these cases, yanking a drive right in the middle of the expansion, all the things that could possibly go wrong. So we have several tests that will do that. It'll run the test, and we have a new tunable so that we can actually pause it in the middle. So because with the test, you're running with small pools, and so the time to reflow is not going to be that long. So you want to make sure you catch it. So we have the ability to stop it right in the middle of doing its stuff, and then we can take a disk out, offline a disk, resilver it, do a scrub, do different things in the middle of those. And so those are, I think, important to cover all the sort of the edge cases that could show up in this feature. And then of course negative tests. When you're in the middle of an expansion, you don't want to be able to start another one. So the negative test, make sure that we're not doing those things at the same time. Like you can't do a checkpoint while you're in the middle of an expansion, for example. And then we also added a test. Matt had mentioned that space is not used, although with the caveat, FreeBSD with FAT and MBR partitions, there wasn't enough space to put the loaders in there, so they used that space. But fortunately, we can detect that. So if that's in use, then you'll actually, when you do the attach, it'll say, I'm sorry, that space is being used. And so you have to go rectify that. So in addition to the test suite, we added for Z-test. Are people familiar with Z-test? Z-test is, we run it in user space, ZFS, and we just basically do everything at once, kind of all kinds of different things, you adding disks, moving disks. And so in that context, we added, you can specify the kind as E-RAID Z, and what it'll do is it'll throw into that big mix of all those things an expansion. And so you'll get expansion, and someone else will be doing trim or all kinds of stuff coming and going. So that's a good use. And then we also did a specific mode where we'll purposely go through the expansion, and at some point, I think it's 25, 50, and 75, roughly, we'll just kill that process. And so it'll come back up and scrub the pool, make sure that it survived a crash right in the middle of the reflow. So that's another good mode. And then to get sort of coverage across all the different parities and sizes of disk, we run it with a script called zloop, which will run Z-test continuously with just throwing a new configuration. Hey, let's try D-RAID. We run a D-RAID run, and we'll do mirrors, RAID Z. And so I added to that mix an expansion, so we can do various runs against all the different configurations, make sure we didn't miss anything. And then finally, we did manual testing, basically VStack myself in that with real hardware. And then as far as performance goes, I was hoping to have numbers here, but ironically, when I was doing the second run, one of the disks died. I mean, it actually died, and I didn't have another spare, so I wasn't able to continue the performance run. So I'm gonna do that on the side once I figure out what's going on with my disk, and publish those as part of the PR. So that people can see it. But it's the same. Well, actually, you have a slide. No, okay. Well, I'll finish up the testing thing. So for the zloop, you can see this is a real run where basically it'll just throw out, like in the first one out of the gate was RAID Z expansion, and it tried it for in this case 11 disks with triple parity and A shift 9, and then in another run, I think there's one on there. Yeah, it's going to use 4K. So you get the mix running. You just run zloop, and I've run this for hours on end, and occasionally you'll see a bug, go chase it down. Same thing for the functional test. I don't know if anybody ever looks at this output, but if you're doing a PR, eventually you'll get a Z-test failure or a test suite failure, and you go look at it, and it'll tell you which test failed. Go look at the logs. Okay, for performance, I don't know if you wanted to speak to this, but basically the takeaway for me, like in running this, is that the read is slightly slower if you're reading the old original data, because we have to bring it into memory and copy out sections. So there's a little penalty there. And writes obviously improve. So did you want to speak to this at all? Or
no?
Okay. So like I said, I'll have some numbers, some more newer numbers with 4K sectors. I think this was 512.
Yeah.
And then finally, this is our hopefully final report, the final talk on this. The PR is out for review. We've had some great review feedback, and we're waiting just for a little bit more, which I'm hoping will wrap up possibly tomorrow during the hackathon. For future, the speed of the reflow, we can improve. There's some things we can do to improve that. Obviously, maybe doing multiple drives at once. If you want to add 2 drives, you don't want to have to wait 12 hours and then wait another 12 hours. Maybe mix that together. But these are all like future things we could do. And D-RAID and auto scrub and rewriting existing blocks was new. I've already seen in the discussion board, people were already coming up with scripts to do that. But basically, you just have to copy the data or overwrite the data to get it to use the new parity ratio. Pretty much it. Q&A.
Yeah, and I'll just mention the right side of the screen here. We get a lot of cues. So some proactive A's. You know, this does a lot of cool stuff that people are like, oh my gosh, wow, it's amazing. It must also do whatever. You could easily since you can do this, clearly you can easily remove disks from my RAID Z. Like, no, nope, that is totally different and perhaps impossible. So yeah, we're not defragmenting anything. It doesn't require the mythical BP rewrite project, so you don't get any of the like other mythical benefits from that. But the stuff on the left here, future work, those are all things like D-RAID expansion that would fall very naturally into this design, but we just didn't do it in this project. It's already taken 6 years. And like for at least 4 different companies, you know, kind of taking the lead on this. So it really has been a really big collaboration among the industry, and we're very thankful for all these companies sponsoring the work, and hopefully it'll be coming to you soon. I'm hoping that the emoji here, it could be interpreted either as like, we're praying, please let this be the final report, or it could be interpreted as high-fiving, because it is the final report, because we're going to get all the people into the room tomorrow to get it reviewed and get it integrated, hopefully. And then we'll really be able to do the high fives. Okay, yes, Q&A now. Wait for the mic so that they can hear you, thanks.
So just how far can you expand? Like expand once one disk and then again and again and again and again?
Yep.
255?
Yeah, I think the limit is the same as the overall RAID Z limit. So I think even without this, you cannot create a RAID Z that's more than 255 wide. And that is still the case. Can you pass it back there? Thanks.
VDEVs at once?
So like if you have 2 RAID Z VDEVs and you want to add one here and one there, the design, like the fundamental design would allow that. It's pretty straightforward, but for ease of implementation and also like ease of administration and kind of observability, it's a lot easier to like for observability, from an observability point of view, to just be like, here is the one expansion that's going on, versus having to be able to tell you about each top level VDEV. Oh, this one is 1% done and that one is 17% done. Even though like, yeah, in theory, like those are independent resources. You could do it and it wouldn't really hurt performance, but consider that on the future work if somebody wants it badly enough. Other questions? Go ahead.
Is it authentic from a performance perspective, such that if one has an imbalance VDEV and oops, they have an extra disk here, they could correct the others, will it be indistinguishable in the performance as if it was always set up correctly?
With the exception of reading the old data as shown here. So like reading the data, the stuff that was written before the expansion, it's going to continue to be in the old layout. And also because we've kind of, if we go way back, like we've made everything go diagonal. There's an earlier one that makes it much more clear. My first one. Yeah, so like if this was all one logical block, then this is kind of what the layout would look like, where the parity actually ends up on all the same disk. And so when you go to read this one logical block, you only have to read from disks 2, 3, and 4. You don't actually have to read from disk 1. After the expansion, the parity is now kind of diagonally across. You see like it's on the last disk, 5 is on the last disk, 9 is on the 4th disk, 13 is on the 3rd disk. And so when you read it in, we actually have to read from all of the disks and then like, you know, tease apart. We don't need the parity, but we need to glue things back together in the right way, the B copy that he was talking about. So yeah, there's like this little performance hit of reading those old blocks. But I think to your specific question about like, oops, created it with 4 and then I want to add 5, that wouldn't really apply because you don't have any space. You know, if you catch it soon enough, then you wouldn't have any space in the old format. And even so, like that performance hit is like pretty minor. I think in this example, it's 2600 versus 2300 megabytes per second. So that's like 20%, 15%. Yeah.
Is there any impact on fragmentation when you start to replace the old data?
No, there's no real impact on fragmentation. I mean, obviously, when we do the reflow, it's just like preserving whatever fragmentation is there, and all the free space is in one giant chunk at the end. So that's nice. When you free stuff that's in the old size, and then you're allocating stuff in the new size, I mean, it might, if your data is extremely regular block sizes. So like, if you're doing the one, the case where it might matter is where you're like, okay, I have 4K sectors and all of my data is only 8 kilobytes. And so like, I've allocated exactly 3 sectors and now I'm freeing it and then I'm trying to allocate. Well, you might think you're going to try to allocate 4 sectors, but there's additional constraints where the allocation size actually has to be a multiple of p+1. So like if you're on, RAID Z3, you're always allocating a multiple of 4 sectors anyways for a given logical block, right? So the more typical use case is like my blocks are big and I have like record size 1 meg, and yeah, like it goes down and now I'm actually allocating, it gets, well, if you have compression, then your block sizes are going to be kind of all over the place. And so you have little minor bits of fragmentation where it's like, some of my compressed block sizes are 300 kilobytes and some of them are 350 kilobytes. And some of them are 400 kilobytes. And now it's like, it's going to be kind of the same post expansion, but instead of being like 300, 350, and 400, they're going to be like 250, 300, and 350 kind of spread out over a slightly smaller range.
Aren't you living like individual sectors? For example, you're overwriting a lot, and now it can fit into less space. Because, for example, you have multiple stripe block.
Yeah.
And now we can fit into less sectors.
Yeah.
So that will leave like some sectors.
Yeah. So like, in theory, I can see what you're getting at, where it's like I have a block that's 300 kilobytes, and then I touch it, and then I rewrite it, and now it's 250, and it leaves like 50 kilobytes of free space there. That's like not a very useful size. But the reality is we aren't rewriting in place. We're like freeing that old 300 kilobyte chunk and allocating a new 250 kilobyte chunk, and you can't like reuse it in the same TXG. You're probably going in and allocating it from the giant unused chunk of space at the end that we created as part of the expansion. So as long as you're doing that like a bunch, then you're going to be filling in the free space at the end. You're going to be freeing up a bunch of space in the middle. And yeah, you're freeing up a little bit more than what you're adding at the end, but it's still like a giant chunk of free space because if you're like overwriting some one big terabyte file, it's going to allocate like 1.2 terabytes at the end, and it freed 1.3 terabytes from the middle. And so the fragment is, there's really no significant fragmentation there. Yeah, George.
When you're in the middle of doing a reflow and you lose a disk and you pause the reflow operation, let's say the disk you lost or one of the original ones, I'm assuming that the new disk that you added, the space is still accessible and allocations continue doing that. Is that true?
Yeah, the new disk, I mean, it's getting allocations, but the new space is not available yet. So, in the middle of the expansion, whether you've lost a disk or not, we're still doing, we're still doing reads and writes, and the new disk is involved in those for the space that's already been copied, right? So like we've copied some amount of the space and moved it to this new locations, which includes being on the new disk, right? So if your read happens to be from like one of the beginning offsets that's already been copied, it might be reading from the new disk. If the read is from like a later offset that hasn't been copied yet, then the new disk wouldn't be involved because we haven't moved it.
And writing new allocations wouldn't actually go to that new disk?
Oh, writing out, so writes kind of work the same way, where it's like you do an allocation, we're still allocating using the old stripe width, and that could be allocated from the part that's already been copied or the part that has not yet been copied. So if it happens to be in the beginning of the disk that we've already copied, then yeah, like that space may involve the new disk, and so you're doing a write to the new disk while you're in the middle of the expansion. Yeah. Any other questions? All right. Well, thank you all very much. Putting my MC hat back on, we have, I think maybe a little bit longer break now. We'll meet back at 2:50 for a talk by Sam Atkinson.
Yeah. No, like until you like the full space knowledge on the end of the form diff, you have a whole bunch of like unused space in the middle, but we're like copying stuff into it, but you wouldn't want to like do an allocation there because we're getting the overwrite extension. Yes. Yeah, that's why I'm asking. Like, could you get to a situation where it's like now you input that disk and now you have no space to reflow? Yeah. So basically, every IO, it looks at every row of that IO. Is this row already copied or not yet? Or there is no like it looks like, oh, this row has been partially not copied. So it has to be the way. So both old and new. Yeah. And there's like, of course, it's blocking all the stuff. It's very, very visual, like their space. Right. Yeah. Yeah. So you might have to do the right to the like scratch space as well as the normal space. That's why we need all these like test points where you can pause it. It's a scratch space. Oh yeah. So I have used this scratch space for extremely long projects, which is that I created this image that is a writable TXT fat DMC pool and at the exact same time, where the data for the fat and TXT files lives inside of that machine.
So there is a function that's called, and it's a no-op for Linux, but if you want to fix it, to say like, oh, it's all special things.
Well, I don't really think it's trying to fix this one where it's C, so I don't think it's actually a problem. But it has been used before. But not
now, yeah. So if you haven't published it,
I mean, I remember actually when I was writing I know. While I'm on maternity leave, like, oh, that's like, I'll work on this. I did. But, you know, it wasn't really that hard. Now, you know, it's like, I was almost done 5 years, almost 5 years ago. And then it's just like you know, not very level, but with, yeah. So basically, like, because you can extend it multiple times, like which each extension.
So we're going to update a lot of those documents.
If not, it's I don't know. Like it's in the Because yeah, one of the other small, like the 16K slot. Basically, like, because yeah, like for it might start on any given drive, and so the current might be on any given drive. There's like then you can ask, well, it might be extremely regular. Then you could and that was a problem, and there was a good to like work around this. Theoretical problem. But that only happens on basis two, because by the time we get to basis two, we realize that this is not actually a real world problem. It's like exactly. So like you can't, it can only be regulated to some authority. If you're gonna have like some other application gets started there, and so in practice, we would be able to actually we always you know any rated thing we have like you actually have a system. So pretty like something that was thought about and now we have that on that. There's like it's a 4 megabyte space. We're using 3 megabytes of it, oh, yeah, the reason is just that when you have more separation between where you're reading and where you're writing, then you're going to make more progress before having to go out the instructions. So then you're more racing play, and it also you know, so we are, even though we are like overwriting, crash, but then going back to yeah. In practice, like, it takes so long to do that even if once they can get it, like, it would matter. We're all doing it's like, you know, space and like, well, it's kind of more, and then like when it gets from one reaches the other, then it's just like if you are in a situation where like if you realize you need to and your sector size is then you can run into situations where that like 254, 255, and my sector size is going to be short, then it's going to be like, you scratch space about the unit, but it's going to have this thing where well, you have to know like per drive. So we have to make it like per drive. Yeah, means that you need in square space. So like each drive has to be able to get like n drives. So as you get more, you need more space on each drive. Almost enough. You need all the drives. You need scratch space. So like basically, yeah. You need scratch space. You need like like 100 wide. You need 100 times you need 2,000 sectors of space, which is 100 sectors. So like when you change 5 wide, you need 205 sectors on each disk. More than 8 kilobytes, 16 kilobytes, then you might run into this with the like 200 wide. Given that nobody uses 255 wide and like it's very rare to find anyone. Good job testing this. We're creating a so in the slides I showed, that's if you have then it's but if you go to okay, then it's like you need essentially 160 CPU that you're making 160 and it goes like right now, like we can just going forward and doing it one sector at a time until we run into all those items until we right. I wanted to do like one big yeah, exactly. Kick it off, wait for the weekend to see. It's like you go to 6 years, very low. I mean, it's just one. But there's one. If we were smarter, we could like it's kind of like the because you can't have like two sectors in the same period. You're always with this. I just kind of He's just making drivers that would allow them to do capacity with buffers at one stage. That's how it
All right, guys, please come have a seat. We'll be starting momentarily. I have your presentation here, but I don't know how to use. Windows or PowerPoint, so. Okay, great, thank you. So next, please welcome Sam Atkinson. He's gonna be telling us about how you're using OpenZFS at scale at AWS.
All right, good afternoon. My name is Sam Atkinson. I'm a senior software development engineer at AWS. I've been with Amazon for about 5 years, mostly on Amazon FSX, which offers OpenZFS as one of its offerings. So I'm going to be talking mostly about OpenZFS in the context of that and its relationship with AWS. Some of the things that we've learned and been challenged by in the last year, and some of the cool things that our customers are doing with OpenZFS on AWS. So for those of you that were here last year, my colleague Stabdi presented on the same service last year. So I'm going to do a quick refresher on what is FSX for OpenZFS, what is FSX, talk about trying to focus on some of the new additions, and then how we've operated OpenZFS, some of the things we've learned, and what cool things our customers are doing. So FSX was first built in 2018 to serve a gap in AWS file storage. We had cloud offerings for file server or for file storage in AWS already, but realized that there's like many things, not a one-size-fits-all solution. So we built FSX, File System X, where X is your choice for your workload. It's your type of file system. And so today we have 4 offerings in FSX: Windows, File Server, Lustre, NetApp ONTAP, and of course FSX for OpenZFS that I'm going to be focusing on today. So the goal, with FSX is just to combine the best of AWS and the best of these industry standard, some of the most popular file systems out there. We fully manage them, we administer them, and then we pass on all of the benefits of AWS that you're probably used to: high performance, durability, security, cost effectiveness, etc. So why bring FSX for OpenZFS into this? Of course, choices were out there. Why this one? So we looked at some of these customer workloads that maybe didn't quite fit into the mold of other file storage services in AWS. Some of them listed here. These high performance databases, source code version control, ML, AI, EDA. We kind of noticed some patterns in these where it really came down to 3 things. First, a lot of these workloads, a lot of these customers needed extremely high performance, very latency sensitive in a lot of cases. They were a lot of times needing NFS, and they a lot of times didn't need the full suite of enterprise features that you'd get out of maybe an ONTAP or a Windows. And so there's an opportunity there to give a little bit of a better price performance ratio with a different offering. And thus we brought in FSX for OpenZFS to fill those capabilities, and then also provide some of the enterprise oriented features that OpenZFS makes available today, quotas and compression, etc. So couple just given things, that NFS, the familiar data access, customers were used to it, needed to remain NFS. So they have their infrastructure in AWS, in an AWS virtual private cloud, and they just need to drop in a replacement for NFS. And so we bring in FSX for OpenZFS there. I'm going to talk a little bit more about the performance and how we deliver that, but just high level, this is kind of what we're looking at, the performance that we deliver on our top end today. Because we sort of went into this with the tenet of trying to balance simplicity with capabilities and performance, etc. We chose to integrate most of the FSX OpenZFS, or most of the OpenZFS features, make most of those available via the AWS APIs. So the Amazon FSx service has a set of APIs, just like any other AWS service, where you can choose to configure different parts of your file system, do things like enable different types of compression, change record size, many things that you'd be used to doing in common ZFS tooling today, libZFS, et cetera. So we picked this set just because customers asked us for it, the most. It was most important to them. It's not exhaustive, obviously, but it's the set that was most important to them, and so it's the set we brought into our API. So it's kind of the overview recap of what Stabdi talked about a little bit last year. So what's changed in the last year? A couple new additions. So previously we had a single AZ, a single availability zone deployment. It was not highly available. Just essentially a single file server in a single availability zone that delivered great performance, but we improved on that this year. We improved on the hardware with what AWS made available internally to us, and that we wanted to pass on to our customers. So it looks something like this now. Performance primarily dictated by a front end and a back end link. Of course, front end being to your NFS client, and then back end to a virtual disk in AWS. One of the really compelling things for customers in this is that back end link doing 80 gigabit per second. It's 10 gigabytes per second sync write, persisted to disk, which a lot of customers have been really happy with, being able to deploy that rapidly, get that kind of performance. You'll also see we've added L2 ARC. We didn't have an offering with that last year. And so being able to take advantage of the L2 ARC with 170 gigabit per second front end link, it's also been pretty advantageous for a lot of workloads. And then we've introduced just a few months ago a multi-AZ, multi-availability zone deployment, which is highly available. And so this is an active passive configuration where we have an active in one availability zone, one group of data centers, and passive in another. Again, we have the same backend link that's dictating a lot of the performance, and on the front end we have a router deciding which is the acting primary, and then we perform replication again also over a 170 gigabit link, and that permits the full 10 gigabytes per second sync writes to durable disk, even in this multi-AZ offering. So just kind of what it looks like when we have a failover. Say availability zone A is or at least the file server in availability zone A is down for maintenance, what have you. We're failing over to make the file server in availability zone B the acting primary, and issue all writes there. Where afterward we'll see resynchronization and the preferred primary fail back. Another new addition, we had a lot of customers ask for this, was a CSI driver, a container storage interface. This is used in a lot of Kubernetes-based container workloads. It just makes it easier to provision, manage shared storage in one place. It's just a common pattern in a lot of these Kubernetes-based workloads, so that they don't need to work with a bunch of different sets of APIs and frameworks to provision storage and servers and software, et cetera. It's just all in one place. And so we built this. It's open source. You can check it out. It just allows you to do things like choose which storage you're sharing within your cluster, static and dynamic, just meaning you can choose an existing or create a new OpenZFS for OpenZFS file server yourself. Choose mount options, NFS mount options, take snapshots, restore from those snapshots, all of which is just a natively supported thing in the CSI driver, and then resize your file system. So that's containers have exhausted all the available storage. You can increase the size of your total file system with the same CSI driver. Lastly, in terms of just new additions, telemetry, we already had telemetry for storage utilization by data set, compression ratio, throughput, and IOPS utilization. We've since added just customer visible metrics for CPU and memory. Just keeping with that balance of like simplicity and performance and ease of use. We added these in because we realized that there was more than one signal that customers would sometimes need to know when they exhausted the capability of their provisioned file storage. It's not just those, that front end and back end length that's dictating what they see as performance. Sometimes they need more memory. Sometimes, thrashing the arc. Sometimes high enough IOPS workload, you're utilizing all the CPU you have. And so we started giving that to our customers. So that's our new additions. Using F6 for OpenZFS, it's because it's all in the AWS set of APIs. You'll see a simple command line interface like this, where in this example, I've just chosen to provision 400 gigabytes of storage with a throughput capacity of 128 megabytes per second. After a few minutes, I will see a fully available file system that I can now work with, etc. So my response here, you'll see I didn't provide a disk IOPS configuration, but just for workloads that maybe have not as much throughput needs, but are more IOPS oriented, maybe a database or database-like workload where you might need more disk IOPS than you would otherwise need, small IOs, that kind of thing. You also see this root volume ID, which is it's a kind of a weird thing that it's called a volume, but it's an overloaded term. The volume in FSX is an equivalent to a file system data set in OpenZFS. And so this root volume ID is the root data set on a Z pool. And so on Amazon F6 for OpenZFS, that Z pool is always called FSX. And so your root data set is always /FSX. So if I want to expand on that, I want to create a child volume or child file system data set from there. I can choose to pass in that parent volume ID to a create volume call, choose a compression type, choose a record size, choose a name, and then I'm getting back a volume path, with that /FSX. I've created a child volume, and within a minute or two, I can use that. You'll see I can also set some manifest export options here. It's very similar to what you'd see if you were provisioning your own NFS server on Linux, very similar. Change your server-side mount options, make it read-only, make it async, do whatever you want. Choose the networks that are allowed to mount this volume, this file system data set, etc. So another thing you can do just in terms of administration is manage maintenance and patching. So we manage maintenance during a maintenance window of 30 minutes. It's once a week. You can update that maintenance window. What are we doing during that? We are doing routine software patching, security vulnerabilities. We're upgrading the OpenZFS version after sufficient review, performing if any hardware maintenance needs to be done, we're doing that. How are we doing it? With our new multi-AZ offering, we're just doing that failover that I showed you, which is a less than 60-second IO pause. So your workload is just seeing a pause, it's seeing failures. And so that's patching. How are you protecting your data? You are doing it most likely in one of two ways. You're either using an OpenZFS snapshot, which is something that will only exist as long as your FSX for OpenZFS file system exists. You delete your file system, your snapshots are gone. It's a single data set, read-only, instant, obviously, all that good stuff. The file system backup, a little bit different. That's a storage layer backup of the entire file system. Any data sets, any snapshots, any compression settings, all of that is contained in your backup. That's stored in S3, a little bit higher durability, the notorious 11 nines of durability in S3, and that will remain after your file system is deleted. So tons of flexibility there. If you're only running your workload at certain times of day or sometimes week, you can take that backup, do with it, what you will. It costs less, move it around to different regions, share it with different people, and then spin it back up when you're ready to resume your workload. So operating this service, we've learned just at scale mostly meaning just the sheer number of file systems that we're managing, that it's impossible to do all of this with automation. Obviously, there's always bugs in every kernel upgrade, and not always in every OpenZFS upgrade. A lot of times there's not, but it's never, things are never perfect, and our automation is never going to catch everything. So we automate what we can. We spend a lot of time working on automated monitoring tools that run on file systems, monitor file systems, and then we spend a lot of time building sufficient internal metrics and dashboards that we review on a daily basis. We're looking for phase changes in performance, looking for outliers in metrics, and then going and investigating where it feels appropriate. Some of the learnings and challenges. So just automated testing and qualification. When we're getting those new OpenZFS releases, we feel that OpenZFS upstream release velocity is high. It's fast, and that probably might be a surprise to some of you that feel that way. But there's a lot of file systems out there that we offer that don't have near as high of a release velocity. So keeping up with that, building testing automation to pull those in is hard. It takes time, and so we've had challenges with that, and luckily we've found regressions before, small regressions that were of no impact to any customer of ours, but it's hard. So we've been working on building automation to pull those in and sufficiently test and qualify them. So we're constantly upgrading and patching existing file systems. So making sure that a new OpenZFS release is going to work with the block layer layout of an existing file system. Obviously, something that is tested by all of you for the most part, but we do the same just to make sure that for any file system out there in the wild for us, that still holds true. User and group quota lookup. This is just an interesting challenge that I wanted to share. We had a problem a little over a year ago. We noticed that some specific testing workloads we were running were causing a deadlock in ZAP Loctor on ZFS writes. This was super small. Write IOs, extremely high IOPS. A lot of times we would see it more often with really compressible data. So we're hitting ZFS write really hard, and so we started seeing this deadlock. We'd only ever see it in this code path within ZFS IDE over block quota. So we submitted an issue report. If you want to learn more about the deadlock itself, you can go there. But we decided this year to sort of step back and ask, like, why are we only seeing this in this ZAP lookup in ZFS IDE over block quota? So we used some BPF tooling, which was fairly new to a bunch of our team, to start looking deeper. So we tried to figure out what else is using the ZAP here. Why are we never seeing this deadlock with anything but ZFS IDE over block quota? So we find, okay, there's only 4 objects here that are being queried for a ZAP lookup in this, ever in this test, and we found that, okay, these 2 objects are indeed the user group and project quotas. And we were confused by this because we don't, in this test and in these file systems we were spinning up, we were not using user and group quotas. So we were, confused why there would be a synchronous lookup of the quota usage during every single write, which is what it looked like. So, just to be sure, we did just another little one-liner BPF lookup here to make sure that we were only seeing this in ZFS IDE over block quota, which we were, and so we were wondering what's going on. So FSX, as you saw when I ran that create volume command earlier, is defaulting user and group quotas to be unlimited, and in our automation, what we're doing is no matter whether the user passed it or not, we're passing a value down to ZFS to set the user and group quota. So that meant we were explicitly setting a user and group quota to be unlimited if they didn't provide it. So every single file system had a ZFS set quota command run on it. And so we were explicitly setting user and group quotas, meaning the quota zap object was explicitly being created and then checked in every write, even though we weren't using quotas at all. So we submitted a pull request to make that behavior consistent so that when we, when we create or when we tell ZFS to create an unlimited quota and all there are unlimited quotas, we can just drop that that zap object. Same with, if I had a legitimate, non-zero, non-unlimited quota and I got rid of it, again, it would drop the zap object if I got rid of it. So the other big impact this had was on performance. So whenever we would see this deadlock, we're completely just totally locked up on CPU because everything's just spinning on this debuff find lock. So the flame graph of CPU looked something like this. And so we were, performance at that point was completely bottlenecked just on CPU. And so afterward, with these quotas actually disabled, we were seeing some huge differences in performance for this specific type of workload, where we were, when we had compression or when we had quotas completely disabled, we were seeing some, up to 3 times the IOPS achieved on sync writes, double the throughput in some cases on sync writes. So it was a big, for a lot of our customers that aren't using group quotas, this is a big improvement. Yeah. So let's talk a little bit more about our customers. Just coming back to these types of workloads and patterns. So, again, these databases, these small IO, really latency sensitive workloads, the dev tests that are requiring that like snapshot clone pattern. What are they looking for? So top 2 here are sort of things that we can work on and are on our radar. A lot of times we see customers wanting more insight into that disk, that backend link. What is our utilization on that actual disk? I don't want to just know how many IOPS ZFS is doing or how many bytes of reads and writes ZFS is doing. I want to know what the disk is doing because it's not always the same. The other is more flexibility with snapshots. They want to be able to move snapshots around, do full, non-clone copies of them, move them from file system to file system, back them up forever. So we've had a lot of customers ask for that. The bottom 2 are ZFS, more OpenZFS related challenges and asks, maybe some of which, and we'll see if I don't know, I'll give them a shot tomorrow maybe. But default user and group quotas, just being able to set a quota for any user ID, GID that doesn't match one that they provided. And then user and group quota utilization visibility. This one I think is interesting because it's, it's sort of a gap in the, what we expose in the API versus what ZFS tooling and libZFS exposes today, where they can set these quotas in the API, but getting them is much harder. Because we're not exposing the entire file server to them, libZFS to them, utilization visibility is hard. And so we've looked at, different ways of maybe doing that in .zfs directory, maybe. We'll see. I'd love to chat with some of you about that. But that's something that the customers have asked for. So let's talk about 2 big customers that we have that are kind of exciting workloads. Life is Tech is in, they do educational services. And so they offer file storage for a lot of elementary and junior schools in Japan. So they have these small file workloads that are a lot of times driven more by their students than them, but performance matters, latency matters. I think, the users in that space maybe a little bit less patient maybe. So this, latency latency say mattered to them, performance mattered to them, and they were hitting bottlenecks on their existing storage system. So they moved to OpenZFS, to FSX for OpenZFS. They achieved that stable performance they were looking for, lowered their operational load because they weren't having to do patching, weren't having to do backups themselves, all of that. And so their one of their SRE group managers here was talking about how they improved performance by 90%, reduced cost by 75% over their previous offering, and then were able to, really simplify scaling the performance of their file system during different times of the year, and changing scaling the storage capacity as needed. So did this for about 500,000 students across Japan. The other is Vela Games. They're a game development company that does a lot of their builds in the cloud. So they're doing a lot of cross-platform builds. They're doing a lot of parallel builds where they're trying to use the same artifacts in multiple builds. And so they use this build graph tool to help coordinate these jobs, parallelism, and cross-platform builds. And their storage system was becoming their bottleneck. So they moved to FSX for OpenZFS. And they were successful in delivering the performance and latency and cross-platform access that they wanted, being NFS, just giving that cross-platform access. And so they were able to have success there. And their technical director here, infrastructure and operations, talking about how they parallelize, reuse assets quickly, just with snapshot clone pattern. And then they were able to cut down their build time by 60-ish%. So what's next? We're looking to get more engagement with the community. We've tried to do that a little bit, in the last year. I know Stabdi, my colleague, mentioned that a little bit last year, keeping up with issue reports that are relevant to us. We're trying to get more AWS engineer hours in OpenZFS code, which is challenging, but we're picking up on that. More upstreaming bug fixes and improvements. We went over a couple, but trying to get even better about that in the future. And that's it. So any questions?
Yeah, so I have two questions that I want to ask. The first is, are you using any ZFS storage configurations on your backend, or are you just relying on your own internal resilience and redundancy features?
So yeah, for redundancy and durability, we're just relying on underlying internal AWS storage services.
Okay, and then the second one is you talked about how you have snapshots as an option within FSX, and then you can do a whole pool backup into S3 as your alternative backup solution.
Yeah.
Have you considered persisting single snapshots in S3 with something like set and receive?
Totally. Yeah, I think we've considered that. I think it's something we'll absolutely consider doing in the future. So yeah.
So you just fail over, right? From one zone to another. Is that to deal with a problem or?
Just high availability. So in our existing single availability zone offering, if we, for example, were doing maintenance, if we had a hardware failure or needed to patch that single file server, customers are seeing up to 10 to 20 minutes of potential downtime during that. And so with the multi-AZ offering, they're getting a pause instead of a downtime.
Meaning you have observed issues?
I mean, in AWS, just the scale, these failures do happen in availability zones. And so generally customers are, we talk to them about architecting in a way where if they need their workload to be highly available, if they have, customers that are using their product 24/7, architecting across multiple availability zones. And so it's a common solution to that problem of, you know, when a failure happens for whatever reason, it could be a single drive failure, it could be a memory module failure. Just having the entire thing fail over to a secondary availability zone.
So what in our company, what we are doing is that sometimes that we're facing the issue of IOV. So basically that's caused by architecture. During that time, with the problem happens, like we got a high IOV, like 40% something. Terrible, which during that time it was low response.
Yeah. I think we used to. I know Satabdi last year actually spent a couple of slides talking about all the tunings we did on Arc, because we did have some trouble with that initially. You know, with arc utilization and pruning causing issues sometimes, but we put in a lot of time into tuning these just right for our different configurations, and we've since taken care of that problem. So we haven't observed that with customers lately. You know, unless their customers will sometimes see if they say under provision their file storage, their file server, they'll see it, but we've pretty much taken care of that with what's
So your ZFS, the zipper is built on the physical drive, not the AWS virtual drive.
the pool itself, the persistent storage is on the AWS side virtual drive.
Oh, virtual drive, not the physical drive.
I mean, it's backed by physical drives.
I know.
But yeah, but it's an AWS internal virtual drive. Yeah.
Okay.
Two questions. One on the performance side. So you had a slide which showed 1 million NFS IOPS, right? So given your backend cannot do that, so I assume that's all coming from cache. And is that on a single instance? If it's like, is it a single EC2 instance it serves that?
Yes, it can serve that to a single EC2 instance client, for example, if that's what you mean.
No, the server side. So
the hardware we use, we don't usually disclose like what the hardware is. It is a single server though.
Okay. Got it. Second question, for the HA solution that you have, do you use safer assembly for replication?
I can't disclose that one either, but we do fully synchronous replication, so a sync write when it's active, it's on both disks, in both availability zones. Sure.
So you're talking about your, so you did some testing. You do some testing when you pull in ZFS updates. Is that primarily performance testing that you're concerned with, or is there any other kind of testing that you do?
There are a couple of logical tests that we do, but they're mostly for things that we've run into in the past where it's like we never want to hit this again. Make sure we have a test for it.
So have you considered pushing those kinds of things back upstream to the community?
We've talked about it. Honestly, that is probably some low-hanging fruit that we could do. Yeah, it is a lot of mostly performance testing, but still, it's a lot of it. We're driving the workloads with public AWS hardware in most cases, so they could still apply.
So, which Linux are you running ZFS in?
The Linux version, I can't say that either. I can't disclose that. We run Linux, but yeah.
You put it into that Linux. It's not the ZFS that comes with it.
Correct. All right.
Thanks a lot.
Thank you.
All right. We'll have another break and so we're a little bit ahead of schedule, so we'll meet back here in about 15 minutes. Thank you. One more talk. Where's an error in this thing here? You're supposed to have, it's fine, there's plenty of time. I probably just typed it in wrong in the. Sorry about that. Yes, you have 50 minutes. Let me get your slides up.
Is this one?
It seems like it.
I'm having a remarkably hard time floating on its own.
Yeah.
And like when it changes pages, it's pixelated for a minute.
Yeah, and like maybe I should have swapped it out for my only 8-year-old.
Yeah.
My old 2 generations old laptop is there, but
this one is already hooked up.
it's you know.
Yeah.
All right, welcome back. Please have a seat and we will be starting the last talk of the day as soon as the computer slideshow starts. All right, please have a seat. We're almost at snack and drink o'clock. We have one more talk. Okay, there we go. All right, so please welcome Paul Dagnelli. He's gonna be telling us about the shared log pool.
Good afternoon, everyone. So as Matt said, my name is Paul Dagnelli. I am a software engineer at Delphix. This is my 10th developer summit. I'm really happy to be here. It's been really awesome. Thank you. It's been really awesome to get to be a part of this community and come here for so many years and get to interact with these people and share this time with all of you. So that's been really great. I've given a couple talks in the past about redacted send receive several years ago, and then about Metaslide performance a couple years after that. And today I'm going to be talking to you about shared log pools, which are a project that I've been working on for a little while. So we're going to start with some technical background so that you understand all the parts of the system that you need to in order to understand the new feature. So we're going to start with the ZIL. So ZFS, as we probably all know, is a tree-based file system. So when you update some data, you have to update the parts of the tree above it, and that can lead to some overhead. And so one of the things that ZFS does to reduce this is it batches data into transaction groups. Transaction groups are an efficient mechanism to reduce this overhead, but they're more efficient the bigger they are. So they tend to be a little bit infrequent and they tend to contain a lot of data. So they take a little while to process. One of the jobs of a file system is handling synchronous writes. There are two basic flavors of writes. There's asynchronous writes, where a program comes to the file system and says, please store this data on disk. And then it goes back and keeps doing things. And the file system persists the data whenever it gets around to it. And then there's synchronous writes. For synchronous writes, the program says, persist this data to disk. And then the file system doesn't return control to the program until the data is actually on stable storage. So it's important for the synchronous writes that you have very low latency because your throughput is directly tied to how fast you can complete these writes. These are very commonly used in certain workloads. For example, databases use a lot of synchronous writes because they need their consistency guarantees to be met. And in order for that to happen, they need to actually know when the data is persisted on disk. And so there's sort of an anti-synergy between these two things, right? You want these very low latency synchronous writes, but at the same time, you want transaction groups to be big so that you can be efficient and sync out lots of data at the same time. And so ZFS's solution to this problem is the ZIL, or the ZFS intent log. It's a per file system or per data set data structure that is a chain of ZIL blocks. And these ZIL blocks contain the synchronous writes and other operations that need to happen synchronously. And they're chained together. The ZIL is not a long-term storage solution. When you write data to the ZIL, that's not where it's going to stay forever. Data is only read from the ZIL when something goes wrong. So if there's a power outage or your kernel crashes or something like that, that's when we actually use the ZIL. Otherwise, the data gets synced out normally as part of a transaction group, and that location is where it will actually be read from in the future when the user wants to read that data. So let's talk in a little bit more detail about how the ZIL works. So a synchronous write comes in, we need to persist it to disk. In order to persist it to disk, we need to allocate a block. But when you allocate a block, we can do that from our in-memory data structures. But you also have to write out that you allocated that block onto the disk so that we don't overwrite that data later. But if we wait for that allocation to sync, then we have to wait for a transaction group to sync out. And now we're waiting for a whole TXG in order to do a synchronous write. And that's terrible for latency. So the way we solve this problem in the ZIL is that the blocks are chained together. Each ZIL block points to the next ZIL block in the chain. So you can always use this chain of blocks to recover all these allocations and know where all of your data is stored on disk. And then after you've done this sort of ZIL allocation and written the data into it, when the transaction group with that data does sync out, we advance the head of the ZIL chain. So we move the pointer in the file system from the first block to a later block once all of the data before that block has synced out. Because all the data in the ZIL is in order, in the order that we created it, at least at a transaction group granularity, you can't lose data this way. When you move the head forwards, all of the old blocks are guaranteed to no longer have data that isn't persisted on disk already. So the head of the chain moves forwards, all of the old blocks can be freed, and the data in them is now persisted in its proper location on disk. So let's talk about the case where something does go wrong, where we actually do need to read from the ZIL. So, your kernel panics, your power goes out, something goes wrong, your system reboots and comes back up. So as I said, we have all these ZIL blocks that we allocated, but we couldn't persist the allocation to disk yet because we didn't manage to sync out the transaction group. So we need some mechanism to find all of those blocks on disk and then actually mark them as allocated in the space maps so we don't reuse that space and trample on the data. And so the process for that is called ZIL claim. And so the way this works is that on import, we go over every file system in the pool. And then we iterate over the chain for the file system and mark each block in the chain as allocated. So that way we don't trample on the space that we used for the ZIL. The next part of the process is actually using the data that's in the ZIL so that we get the data that the user wrote back. And that's the job of ZIL replay. This is a separate step that happens when you actually mount an individual file system. When you mount the file system, you iterate over the chain for that file system, and then you apply each record in each of the blocks. You can have several writes coalesced into a single block for efficiency reasons. And so because the data is all in the ZIL already, right, it's still in the ZIL chain, you can just apply these as normal asynchronous writes. And when a transaction group syncs out, you'll get to advance the ZIL chain the way that you normally would, and the system will go back to functioning the way that you intended it. And so that's how we use the ZIL to recover from failures. So the next thing to talk about is the slog. So I mentioned earlier that we allocate these ZIL blocks on your disk. And that sort of leaves the question of where do we do these allocations? Where do these ZIL writes go? So the sort of naive, simplest solution is that they just get stored with the rest of your data, right? On your normal VDEVs, mixed in with the rest of your stuff. But there are some problems with that. The first problem is that as your disks fill up, fragmentation increases, the amount of like big free chunks goes down and your biggest free chunk gets smaller and smaller. And ZIL blocks tend to be a little bit big because you want to try to get as many writes out as possible. And so you want to try to batch things together. And so it can be hard to find good places to allocate this data. And even if you can find good places to allocate the data, even if you have lots of free space, your normal disks are like being used by the rest of your reads and writes. You're doing reads to them, you're doing writes to them. And so there's a lot of other traffic going to those disks that might make your synchronous writes slower. Plus, if you want your synchronous writes to be fast, you probably don't want to use spinning Rust. You want to use Flash or NVMe or other sort of advanced storage technologies. But now if you have to make your whole pool out of those more expensive disks, it's going to be a lot more expensive to store the same amount of data. There's a few ways that you can mitigate some of these problems. So the embedded slog was a feature that was introduced a few years ago to help with the allocation part of the problem. And so the idea there is that there's just a separate, one metaslab in each VDEV. There's a segment of each disk that is prioritized for the ZIL allocations. So that way you basically always have some of this pristine space where you can reliably do these allocations and you can quickly and reliably find the space. But this doesn't really solve the problem with, having other traffic to those disks or needing more expensive disks to get really good performance. So it solves one problem, but not the others. If you want really good ZIL performance, you need a slog device or a separate intent log device. And the idea here is that it's just another disk that you have attached to your pool that is only used to store ZIL data. So this is the way that you get the best performance, right? You have this separate device. You can make it a single, very fast device that doesn't need to be that big because it doesn't need to store that much data. The downsides are that there's more administration work. You now have another device that you need to manage. You probably want it to be mirrored if you really care about your data, because otherwise, if you lose that disk and have a power outage, you've lost all of the stuff that's in your ZIL. It's probably a pretty expensive device because it's another device that you have to buy and you want it to be high-end storage. So there's trade-offs for using this slogs versus other devices, but generally it's the sort of best performance solution. And it's how you solve the problem if you really care about synchronous write performance. So that's the ZIL and the slog from a technical perspective. Now we're going to talk a little bit about the context that led to the work that I was doing. So when most of us interact with ZFS, we have a single system with a single storage pool with a bunch of disks in it. And those disks might be mirrored or RAID-Z or whatever. But there are some situations where you might want to have multiple storage pools on a single system. And I'm going to talk about some of those use cases to kind of motivate what's coming next. And so one context is if you want to be able to move data from one system to another system. And one easy way to do that is if you have like a storage area network or a fiber channel backend that you're using to actually host your physical drives. And so one setup that you could reasonably have in that case is that you have a bunch of different pools serving a bunch of different data that all get their actual storage from the SAN. And they're all busy doing work, but then one of your pools ends up getting a lot more traffic than it previously did. And so you want to move it to a new virtual machine or physical server in order to actually get better performance for that pool and the other pools sharing a system with it. So you can actually move the data from one system to another or migrate them back together if you have ones that start demanding less performance. So there are reasons why you might want to be able to move these systems around. And that's a reason why you might end up having multiple pools on one storage system. Another context that people use multiple pools in is for fault isolation. And this is particularly common for data caching. So if you have a really big cache, you want to store lots of data in it. You don't want to necessarily use mirroring or RAID-Z because you want to get the most storage for your disks. But also, you don't really care if you lose some of the data because it's just a cache. You can always fail over to whatever's behind the cache and fetch the data normally. So you want to have this sort of isolated fault behavior. So you can actually have a separate Z pool for every disk. And that way, if one of the disks dies, all of your other data stays accessible. There's administration overhead to this, but it turns out that a lot of caching software already supports this kind of layout because if you aren't using ZFS, you already have one file system per disk. And so a lot of the caching solutions already support this sort of multiple map point approach. So this is another context in which people actually have several Z pools on one system. And then there's a bunch of other cases, right? You might have multiple pools on a system because you're moving data from one to the other so that you can then physically move some disks from one place to another. If you want to do like a sneaker net approach, if you don't have good networking between two locations and you want to move data around. Or if you have data with very different performance or redundancy requirements, you don't necessarily want to mix it onto one pool because there will be mismatches where, now you have bulk data that you don't want to store on expensive drives, or you have, high performance data that you don't want to store on spinning Rust. And so you might have multiple pools for those reasons as well. And so this picture sort of shows you what the problem is going to be. Let's say you have lots of storage pools on your system. And for a bunch of them, you actually care about the synchronous write performance. So you want to give them slog devices. And so now you have a slog device for every pool that you're using. And maybe you don't want to use like a whole physical disk for every single one of these. So you have like one disk and you partition it for some of them. And so now we're starting to get into some thorny administration problems. How do you do capacity planning? How much of the disk should each pool get? What happens if one of your pools starts to get more demand than it used to? Do you need to like buy more disks and attach them? Can you repartition? And what happens when you add or remove pools? Are you going to repartition all of your slogs now? Are you going to buy new slogs just because you had one new pool come onto the system? So we've created sort of all these administrative problems if you try to have many pools with slogs on the system. And the insight is that this is why Z pools were invented in the first place, or one of the reasons. The goal was to be able to just pool all your storage, and then it would get used by the file systems that need it, and you didn't have to think about that mapping from disk to file system. ZFS would handle it for you. And so the solution to the problem is the shared log pool. And the idea is basically that it's just a pool of slog devices. And then you can have client pools that talk to the shared log pool and actually use it as their slog. So you can see in the diagram here, we have all of our pools from before, but now instead of having their own slog devices, they talk to the shared log pool, which provides slog capabilities for all of them. It's important as part of this project that we keep performance very close to the way it would be with dedicated slog devices, right? Because if you can't do that, then you're starting to introduce big trade-offs between, should I use slog devices? Should I use the shared log pool? And it starts to make it a much more thorny question. So we really want performance that's just as good as we had with slog devices. And then also we want all the simple administration benefits that we get from, using ZFS and having storage pools and having that sort of relatively simple administration of lots of disks. So let's talk about what a shared log pool is. And the easy way to start with that is how you make one and how you use one. So a shared log pool is under the covers basically a normal Z pool. And from a user perspective, it's basically a normal Z pool with a couple caveats. One of them is it doesn't have any file systems, which is a little unintuitive for a storage pool, admittedly. But the reason for that is that we don't want you to be able to store user data in this pool. It's really intended just as a space to store the ZIL data. That's the way it's designed right now. That could change if people really feel that it should be able to store user data, but this was what made the most sense as part of the design. Normal, so, and then it's marked as a shared log pool with a flag in the config or in the pool config. And when you create the pool, a new data structure is created, which is called the chain map. And I'll talk more about what that data structure is and why it exists and what it does later. But here you can see sort of what it looks like to create a shared log pool. There's a new flag to zpool create, the -L flag. And when you create it, it looks just like a normal pool, right? You've got the name, you got the size, you got all your disks, everything looks good. Let's talk about the client pools, the pools that actually use the shared log pool to provide slog capabilities. Again, very normal Z pool, except that they don't have physical slog devices. There's no actual disks, there's no embedded slog. And so one consequence of this is that you either have a shared slog or you have physical slog devices. You can't have a hybrid approach where you have some slog devices and a shared log pool on the same, attached to the same pool. You get to a lot of thorny technical issues if you try to mix the two approaches. So it's all physical or all virtual, no hybrid approaches. The client pools are marked as depending on the shared log pool. So in order to import your client pool, you have to have the shared log pool imported. If you try to import it without the shared log pool, it'll tell you that it can't import right now unless you tell it to discard its logs, which is an existing thing you can do in ZFS, like if you lose a log device. And then the big difference is that your ZIL blocks are actually stored in the shared log pool, right? All of the ZIL chains are stored in this shared log pool, and that's where all that data gets persisted. So you can create a client pool from scratch, or you can import a client pool as so that it becomes dependent on the shared log pool. So here you can see what a creation looks like. There's a new -L flag that you provide the name of the shared log pool, and then client pool name and then disks just like usual. And here you can see what it looks like. You have a client pool with its drives, and then it has a shared log entry, and then the name of the shared log pool that it's actually using to provide slog capabilities. And import looks very similar. You have to import with the -L flag as well, and you also need to provide -M to tell it that you're discarding your existing logs. You won't be keeping that data around because your ZILs are now stored on the shared log pool. That's not a problem in normal operation, because if you did a clean export with your file systems mounted, all your ZIL chains will be empty and nothing will be lost. So you just need to make sure to do that before doing the import to make it use a shared log pool. So there's a little bit of a technical issue with what I just talked about. And it's that the ZIL headers for the file systems are now pointing into the shared log pool. And that's where the actual blocks are stored on disk. So does that mean that we have cross-pool block pointers? Are we now, do we have block pointers on disk now that actually point to a different Z pool? Is that really something that we want to have to deal with and try to understand from the file system's perspective? And then another really big issue is the ZIL claim process that I talked about. When you import the shared log pool, which has to happen before you import the client pools, how does it know where all the ZIL chains are? Because we may not have been able to persist the allocations onto disk. We may not know where that data is stored. So how do we do ZIL claim? How do we find all of these blocks so that we can actually reliably start doing new allocations without trampling on this important data? So we need some sort of solution to solve these problems. And that solution is the chain map that I mentioned earlier. Fundamentally, the chain map is a map from a file system or an object set to a ZIL chain. And specifically to the first block in the chain, just like a ZIL header would be in a normal storage pool. In memory, the chain map is an AVL tree of AVL trees, where the first AVL tree is all of the different client pools that are using the shared log pool. And the second, the AVL trees within that are all the different file systems within a given client. And in the nodes of that AVL tree, you have these pointers, you have the actual block pointer to the first block in the ZIL chain. The on-disk format is ZAP, where the key is the pool GUID and the file system ID, and the value is the block pointer. And so this data structure is created when you create the shared log pool and populated as part of normal operation. So let's talk a little bit about that. So let's talk about first the case where you're creating a new file system. So you have a new ZIL that's about to be created. We need to create the new chain. We need to store it in the shared log pool. And so when you create the new file system in the client, you add an entry to the chain map for that client. And then you allocate the first block in the shared log pool, and you point the chain map at the first ZIL block. You have to pre-allocate the first block of the ZIL so that it knows, so you actually have a starting location for the chain, so that we can do the recovery process. Now, okay, you've got your ZIL. Now you have, how do we add new blocks to this chain? How do we do our actual ZIL writes? So synchronous write comes in. We need to allocate a place for it in the shared log pool. So we just append it to the chain the same way we would with a normal ZIL write. None of the actual logic here changes, except that the allocation takes place in a different pool than it used to. You still update the last ZIL block to point to the new one. You still do the allocation. You still put the data where it used to go. It's just happening in a different storage pool. So we've got the data. It's persisted in the ZIL block. And now it's time to sync out the TXG that the write is actually going into. So now we need to actually do the step where we move the head of the ZIL forward into a later point in the chain. So after the transaction group syncs in the client, because remember, these are two different pools and they have their own sets of transaction groups happening at different times. So after the client syncs its transaction group, it goes and gives a bunch of updates to the chain map. There's a new data structure in the client called the SPA ZIL map that stores all of the updates that it needs to make to the ZILs in this transaction group. Just a mapping from file system to the new ZIL block that the head needs to point to. And then once the chain map has been updated to point to the new location, we can issue freeze for the ZIL blocks just like we would before. The next case is where we're removing a ZIL. We're deleting a file system. We need to free all of the blocks in the chain and get rid of them and remove the chain map entry. And that happens pretty straightforwardly. So again, after the transaction group syncs in the client where we deleted the file system, we update the chain map. There's a new data structure called SPA ZIL deletes. That's just a list of all the deletions we're doing in this transaction group. So the transaction group syncs out, we apply the list of deletes, and then in the shared log pool, we go through the chain, free all the blocks, and then delete the entry from the chain map. Let's talk about ZIL claim, the recovery part of the process, or the first part of the recovery process. So after a crash or a power outage, we're importing the shared log pool again. And when we import the shared log pool, now we have the chain map. And so we iterate over each client in the chain map, and we iterate over each file system for each of those clients, and mark each of the ZIL blocks in the chain as allocated. And so that way the shared log pool is able to do the same sort of ZIL claim process the clients did without actually needing to have their file systems. It just has their ZIL chains, and it has pointers to all of them. Then ZIL replay is still deferred until the clients are actually present. Once the client pool is imported and it's found it's registered itself with the shared log pool, then for each of its file systems, it'll go to the chain map and pull the head of its ZIL chain and replay all the records in the chain, just the same way it would before, except all the IOs are going to this new storage pool. But there's a little bit of a race condition here that you might catch if you're a little bit tricky. So I talked about what happens if you delete a file system, which is that after we sync the transaction group in the client, we go and update the chain map and free all the blocks in the shared log pool. What happens if we crash after we sync in the client, but before we sync in the shared log pool? So then the chain map entry will still be present on disk, and all the ZIL blocks would still be present on disk. And now we would leak that space if we didn't have some way to clean that data up. And so the solution there is that when you import the client pool, when we're iterating over the chain map entries for that client, any entries in the chain map that don't have an actual corresponding file system in the client pool, we immediately clean those file systems up. We remove their chain map, clean up all their ZIL blocks, and prevent that space from being leaked. So you do leak it very temporarily, but only until you start importing your clients again. So it's a short-term problem that will resolve itself. Eventually, when you're moving your pool from system to system, or you're done with a given storage pool, you have a deregistration process where you're removing the client pool from the shared log pool. And as part of that, we need to clean up all of its chain map entries. So we go over all the different file systems in the client and free each block in the chain, just the way we would for each of them if we were deleting that file system. We mark that the client pool is no longer dependent on the shared log pool. So now it can be imported freely without the shared log pool. And then this is all done as part of an export process. So the next time it comes back in, you can import it normally and it'll start doing its slog or ZIL allocations wherever it normally would. But sometimes things go wrong. And so you might have a case where a deregistration didn't happen. Maybe you moved a pool without remembering to do deregistration. Maybe a pool got destroyed by some sort of incident. And by whatever mechanism, you have this pool that never got deregistered. So there's a new command in ZFS that serves as a backup for this. And it's basically a garbage collection process. And the idea is that you issue this command to the shared log pool, and it will iterate over all of the clients that aren't currently connected to the shared log pool. And for each of those clients, it'll do the cleanup process and effectively forcibly deregister the client. And so here you can see what that looks like. So let's say we have this client pool that is a client of the shared log pool, and we export it. If you issue the new command, which is called zpool recycle on the shared log pool, it'll go through all of the clients that aren't connected to it and do the cleanup. In this case, you can see there's a -n flag. That's the dry run flag, which we use in a lot of other places in ZFS. And so that'll actually tell you which pools are going to get cleaned up without cleaning it up. So that way you can make sure that only the data that you want to get deleted is actually going to get deleted. And so that's the other mechanism that we use to make sure that space isn't leaked if something goes wrong and you happen to lose a storage pool. Finally, eventually you may want to delete your shared log pool. You're not allowed to do that if there's any clients currently attached to it, because they are busy using that space. It's a storage device for them. You're not allowed to move it out from under them. Similarly, you can't export the shared log pool while a client is running. So if you try to do it, it'll give you ebusy and tell you that you're not allowed. But if all the clients are disconnected or destroyed, then it'll go through, delete all the chains, free all the blocks, mark itself as destroyed, just like a normal pool would. Any clients that do still exist, if you want to import them again, they're going to need to discard their logs. So here you can see sort of the normal case where you destroy all your clients and then you destroy the shared log pool, and it looks just like destroying a normal pool. And then on the right, you can see the case where one of the clients was only exported and not destroyed. And in that case, if you want to re-import the client, you have to discard the logs. But again, clean exports that happen as part of normal operation with all your file systems mounted won't have anything in your ZIL chains. So an import discarding your logs won't lose any data for you. So that's how shared log pools work. Let's talk now about one of the important things that we wanted to preserve with this, which is performance. And a big caveat at the start is that if you aren't using shared log pools, you won't notice a change when these bits integrate. Comparing before and after for using slog devices or embedded slogs or no slogs, there's no measurable difference in performance. All of the code is gated behind checks that you're using the shared log. So there's no difference for pools that aren't using shared logs. If you are using a shared log, compared to what it would be if you had those slog devices as dedicated slog devices for the pool, you get about 98% of the throughput in terms of synchronous write operations. I tested this a bunch of times, running a bunch of different workloads with a few drives for the normal data storage for the pool, and then a few drives as the slog devices, either directly attached or configured in a shared log pool and attached that way. And the difference was within 2% for almost all of the test cases that I ran. There's one caveat, which is that if you have a lot of different file systems issuing synchronous writes at the same, or getting synchronous writes at the same time, the performance penalty got about as high as 7%. And the problem there is basically that the SPA ZIL map data structure that I mentioned is being accessed by all of these different file systems as they receive these updates. And as the ZIL chain wants to move through, you get all these different things trying to update it at the same time. This can be improved in the future by minimizing what the mutexes need to cover, using more advanced data structures, making other clever tweaks. But for first pass implementation, 93% throughput in the worst case scenario seemed like a pretty good result to me. So that's what it is right now. There are a couple of caveats with this work, a couple of restrictions associated with it. One is that you can't re-GUID client pools. this gets a little bit thorny because you need to like try to synchronize the update between the client and the chain map. And that is technically tricky, even if you try to use something like a ZIL on the shared log pool side. So that's not allowed. Checkpoints are also forbidden in the current implementation. It doesn't really make sense to do checkpoints for shared logs, but it does make sense to do them for client pools, and it will probably get done in the future. But in the first pass, you're not allowed to take checkpoints of client pools because it was somewhat technically complicated to implement. But that work will probably be done in the future. As for what's available right now, there's currently a pull request open on GitHub. I would absolutely love if people took a look at this pull request, whether that's because you're interested in the technical parts of the code and you want to comment on that, or if you have use cases in mind and you want to see how well this will work for your use cases, or you're concerned about the effect this will have on other parts of the system or other features that you're working on. Please take a look at the pull request, get involved, comment, or you can reach out to me, at drinks after, at the hackathon tomorrow, or I'm available on IRC, Slack, email. I'm easy to find on the internet. And with that, does anybody have any questions for me?
From the shared, like SQL detach the shared log to gracefully make it not part of the shared log anymore?
So the way that it works right now is basically that you have to do as part of export, but it might be possible to do it as part of a different operation like zpool detach. The problem is basically synchronizing the cutover from all of your ZIL chains being stored on one device to stored on another device, because we want to avoid the cross like pool block pointer problem that I mentioned, and the trickiness that that creates. So it might be possible to do as part of zpool detach, but it would have to be like a weird zpool detach that forces all of the data out of all of your ZIL chains and then causes all of your ZILs to get recreated. Yeah, you have to kind of quiesce everything in order to make this happen. So right now it's like an export process, and then you do, well, on import, you would come back with normal slug devices.
What's the resulting size of the slug per pool? You showed 240 as I recall, but is it divided equally? Is it something else, or do you specify as a user?
Yeah, so the way that the storage is divided up among the clients is basically that all of them just get equal access to the space. There's no, right now there's no quota system or anything controlling which one gets which amount of space. And part of the reason for that is that by and large, the constraining factor on slog devices is not the amount of storage that they have, but instead how quickly they can respond to IOs. The amount of dirty data that you end up with in a slog device doesn't usually get that big for a given storage pool, because data is only stored on it until transaction groups manage to sync out. If it's important to some use case that we be able to have some sort of quota system, that would probably be possible, where you could have, checking in the shared log pool for how many blocks have been stored in it, and then like make the given clients delay until some of their space has been cleaned up. But there isn't any mechanism like that right now.
Yeah, you mentioned a couple of cases where you need to import with the discard logs flag, and that in a lot of those cases, you probably would have done it with export, or there wouldn't actually be any data that's discarded there. I was wondering if there's some way that we could detect that was the case, so that you don't have to use that scary flag. So there was this kind of scary to be oh, well, I'm discarding the last few seconds of operations, but I'm pretty sure that I cleanly exported and there are none.
Yeah, so there isn't currently a mechanism like that, but it's definitely possible to implement one where if you do, if you're doing an export and it's, after you finish replaying a ZIL chain, we could maybe have some system to detect as part of that, oh, we are doing an export, we've emptied this ZIL chain, there's no dirty data in it right now. Let's mark the ZIL chain as actually being empty in some special way, like storing a whole block pointer or something like that in the ZIL header. And maybe by doing that, we could, and if you did that and had all of your ZILs marked that way, we could detect when you're trying to do the import, whether anything was actually going to be lost.
Yeah, kind of along those lines. If you'd like to get a message back, you wouldn't use the flag, and might tell you, I can't do it because you have dirty data in client X or something like that.
Right.
would be nice to see. And kind of related to that, what message do you get when you try to destroy a spawn pool that has active clients?
In the same way that you would if it had active like mounts and locks held, you get e-busy.
Do you get any indication like busy because these clients exist, sort of messages?
Not right now. So part of the problem there is that like the mechanism for returning errors from the kernel to user land is a little limited, but we could have something in user land that was like, if we get e-busy, check if this is a shared log pool. If it's a shared log pool, get the list of registered clients and display that as part of the error message.
Do you think this opens the door anymore to a different allocation, like algorithm for specifically for the log pool, like a lower latency allocation?
Yeah, I mean, so there were recently changes made to ZFS, I know, to make it so that you can tune allocators more easily with parameters and stuff like that. And related to that, we might want to have something where you can have per pool allocation schemes, where I don't know if we can do that today, but if you could, having something like a first fit approach specifically for the shared log pool to minimize latency would make a lot of sense. That would probably be part of a separate, Don might have a comment on that.
Yeah, we had done that at a previous company, but we were first fit. It's like, you don't need to worry about that's it.
Right.
I had a question on testing it. There's like a spa freeze and it's still test. Did you do something like that?
Yeah, so the way that this was tested was so first there's a bunch of new tests in the ZFS test suite to test like the basic stuff, like make sure you can't destroy a pool while things are attached and all that kind of stuff. And then there's also changes, I think I made changes to Z-test. I don't remember if those are part of the PR. I need to check. But there are changes that like create that use shared log devices and stuff like that. And then for the performance testing, the ZFS performance test suite now lets you create shared log pools instead of using slog devices. You can specify like what kind of slog you would like to use when you're doing synchronous write testing.
Yeah, I was thinking of the test. I think Neil Kerman did it, but basically you could freeze the spa, so it's not going into the transaction. It's just like only in the ZIL, and then you can replay it, compare it, and it's like in the data persist through the ZIL.
Yeah, I didn't run any tests with that feature specifically, but it sounds like that would be good, something potentially good to add to like a Z loop run or something like that.
Well, does the shared log pool know that the client has not done a mount? So the case where, for example, like, you know, we did the claim, but we haven't done the replay because maybe the file systems are set, you know, to not mount automatically. Does that log pool know so that, going back to the case of like doing the dash n, that would be an instance where you wouldn't want to do the dash n because you never did the replay.
So the shared log pool doesn't know what client file systems are mounted or anything like that. That information is purely stored on the client side, and the freeing purely happens, like the updates to the chain map are purely client driven. So it doesn't know whether or not the client has mounted any of its file systems or done replay or anything like that. So that is definitely something else to think about when it comes to like exporting with deregistering and importing, discarding your logs. Some of this is solvable. Some of it's very tricky to find ways to fully protect the user. And I don't know, I would be happy to talk to people about possible solutions for some of these problems because I don't know if all of them are solvable.
Because in case of replay, you should have log recreated, so you could flush the chain and you record the chain is now empty and you could safely drop it after that. It should be doable.
Yeah.
I have other thoughts, like first during reclaim command, you could specify for which pool you would like to reclaim. If you store information not only read but also full name, it would be much more manageable. I think you could just which pool has gone and which is not important.
Yeah,
it would be more convenient to see that. And with some command, maybe it's inventory of what chain or chipping do you have, which are currently connected, which are not. Manage that.
Yeah.
I think I was thinking. I don't know about implementation, how quick that would be, but if you have I'm thinking was it could represent log pool with as another special kind of VDEF. So you could use add, remove command, and other because special like -L argument to import is pretty ugly and special thing like in this case.
Yeah.
You don't want to import export pool for management. It should be much more smooth and another special VDEF. Of course, it would require a number of hacks to make it special, but we already have like indirect VDEF, which is not visible, but it's present there as well. Kind of opposite case of visible, but not there. But
yeah, so this was something that was considered. So first question first about the name versus GUID thing. It's definitely possible to add like a GUID mapping in the shared log pool with the names of the clients or like the last name that they were registered with. And that's something that I can implement as part of the initial draft. It shouldn't be that much extra work so that you can use the name as part of the recycle command. When it comes to having it be like as a zpool add or a zpool attach or something like that instead of an import export thing, the problem again is sort of the synchronization of like when do we make it so all of the ZIL chains point to the new device rather than being stored on the current device. And if you're doing it as part of adding a new VDEV, you're doing it as part of normal pool operations, which means that you have like IOs to your existing slogs already ongoing, and you need to find some sort of way to migrate the ZIL chains over. And it's not impossible to do, but it was sufficiently tricky that I decided that the cleanest way to do it was as part of the import-export process.
I think it shouldn't be that complicated. If you just in a root of your blockchain, you report whether this specific blockchain belongs to the shared pool or it's your local. If it's your local, behave the same as any other blockchain with block pointers and everything. And if it's shared pool, then it's shared pool and works through the blockchain mechanism you described. But that way you could easily combine both, just one data set which is not mounted can live happily on your local pool, another data set that was that last synced and created log after the shared log was created, when you leave shared. You may happily coexist those, you can remove and delete each of those dynamically. I don't see a problem, and I think much more convenient than global switch.
I think one of the problems with it is that you have to, so if you just did it as an attach like that, then coordinating when a given file system would switch over to the new shared log pool is an issue, because you would need like you have to empty the ZIL chain for that file system in order to switch it over. And so we would need some mechanism to like force a given file system to empty out its chain and then recreate its ZIL on the new system, unless all of your existing file systems would stay on your existing slog devices and only new file systems would get slogs on the new thing. Unless you tried to like update the tail of the chain and have that have a special marker to point into the shared log pool. That might be technically feasible, but it seems like it would be a little bit challenging.
Well, I think that already happens when you do normal device removal. Like if you do device removal, you have to get the ZIL chains off. I think that might already happen, like when you're doing device removal and some other operations where it goes through all the ZILs and like discard, like gets them all gone, and then it creates another one. I think there's like a
spot reset log.
Spot reset log. Yeah, exactly. Spot reset logs already does that. So you do have the case where, like you're mentioning, you may have some data sets that are in the old location and some that are in the new location, but they're all kind of like on their way to being in the new location by like discarding the old one and starting a new one by using that spot reset logs. So that might be helpful.
Okay. Yeah, I can take a look at that. Probably not tomorrow because I have other plans for tomorrow, but sometime in the near future.
So with a multiple network, with a shared macro, so this shared macro could be a single point of failure, right? So what happens if it goes wrong?
Yeah, so if the shared log pool itself has failures, I mean, in much the same way that if your slog device dies attached to a normal storage pool, you might have to import losing your logs. And this is something that ZFS already handles. But this is part of the reason why it's recommended that if you care about your slog devices, you have mirroring or things like that. And you can have mirrors in shared log pools. They're created just the same way normal pools are. You could have them be mirrored or RAID-Z or whatever.
Okay, I saw you created the pool, zero, that's right.
Yeah, the example I used was Stripe, but you could use mirrors, you could use RAID-Z, you can use whatever sort of VDEV functionality ZFS has.
You support any layout?
Yeah. Yeah, it'll support any layout that ZFS supports right now, because fundamentally it's just a normal storage pool whose allocations are being like done in a weird way, but the backend all works exactly the same way the normal pools work.
So in your code, is there any like a fallback? If you go wrong, you go back to the data they pour itself to store the DAO records?
You mean like if the shared log pool faults?
Right.
Right now, if the shared log pool faults, the client pools are also going to fault. Because one of what is effectively a device of theirs, or what is functioning as a device of theirs, is faulted. And so they'll go into a faulted state. It would be possible to instead have the data store, like instead have it go to a failback mode where it would try to store the data locally. But you need to do something about the ZIL chains that are already on the device. And you would either need to like recreate those locally or do some other sort of mechanism. So there's nothing like that right now, but it's possible that there you could make a change that would have a more graceful fallback mode.
Yeah, because we run a bunch of servers and time when a slot drive got problem, you will be in a mirror case. That problem basically the for IO which is stored. That's what we observed. Probably said that has been improved. At least a few years back, we got this problem, frequently. So that's why I asked you this question.
Yeah.
If something goes wrong, is there any way to make it keep going?
Yeah. No, that's a good question. I think that's something that could use more work, probably, either as part of this PR or as a separate mechanism.
Thanks,
Paul. Cool.
All right, thanks so much. That was our last talk. So thank you all for joining me for the 11th time. I've organized this conference 11 times. We've had it 11 times. I'm always super impressed by the amount of work and attention to detail from the community on moving ZFS forward. I mean, I started ZFS more than 20 years ago back at Sun Microsystems, and I never would have guessed that we'd still have so many people interested in using and making ZFS better and making it applicable to so many new use cases that we never imagined all those decades ago. Logistic things, so we're gonna have some refreshments on the other side of where the lunch was. And then tomorrow, the hackathon will be here at 9 o'clock. We have breakfast, right? Yeah, so we're gonna have breakfast and lunch tomorrow. If that isn't reason enough to come, then don't dismay if you don't have a laptop set up for doing ZFS development. There's gonna be lots of other opportunities for participation. If you don't have an idea of what to work on, don't worry, we're gonna start the day, maybe around like 9:30, we'll have like a roundtable discussion of what things folks are interested in, what they wanna work on. You can find a team and join up. So I hope to see you all tomorrow, and let's enjoy some drinks and snacks. No, I don't think that we're gonna do any like recording or broadcasting or anything tomorrow. Thank you very much.
I'm glad we figured out why it was making us all sound like chipmunks or
Yes.
whatever.
Well, it turns out I think you were the only one who suffered from that because you were first.
The helium voice.
Well, yeah, wrong sample rate.